All right, are we good? We're good to get started. I love that we always do these big events about high performance computing and then we still have trouble with AV, right? And if you've ever done demonstration tutorials, they tend not to go well live. So we'll not be doing any live demonstrations today. What we will be doing is reviewing a lot of topics at a very high level. And the goal is to come away with a unified story or philosophy on how to use the tools of the cloud world on our bare metal HPC systems and how to use that to make our research more reproducible. And that's going to be what the morning session is. Afternoon, we're going to talk about open source LLMs and controlling your own data and not sending them to the Elon Musks and the Altmans of the world, and keeping your data on-prem and doing cool stuff with it. I'm going to be giving you a lot of technical content, but a lot of it is highly opinionated. And so I'm going to give you sort of a little bit about my background, and you can judge whether it's worth listening to me and where sort of my story comes from. So my name is Chris. I have a PhD in computational quantum mechanics from UT Austin. I was the first class of NSF graduate fellows that got to use supercomputers to do their PhD. And when I finished my PhD, I was much more interested in how I solved the problem than the problem I solved. So I stayed on at UT Austin as faculty, and I was essentially in the research branch of TAC, the Texas Advanced Computing Center. TAC is the largest academic HPC center in the world. And actually, TAC was founded to support the department where I was research faculty. When I joined the department, it was called the Institute for Computational Engineering and Sciences, which unfortunately acronyms to ISIS. So in the mid-aughts, it was renamed to the Odin Institute, named after its founder. And it was created the world's first graduate program in computational science, engineering, and mathematics. And I created the graduate curriculum in computational science there. Worked as a faculty member and researcher for 20 years, did a bunch of cool stuff. Did a lot of stuff in Bayesian inverse problems and uncertainty quantification. And essentially, we became hired guns. Anyone could bring their physics and their code to us, and we would help scale it, improve the performance, run it on big machines, and then do uncertainty quantification, right? You have a probability distribution of input parameters, you pull from distributions, and you generate distributions on outputs to help understand the uncertainty in your simulations. After doing that for a while, if I just sort of chased the computational dragon, looking for the biggest problems in the world to run in, and you end up in the Department of Energy. I was still a faculty member, but I was doing research for the National Nuclear Security Administration. And one day and woke up and realized, hey, I'm helping people design and build nuclear weapons. And it was cool, but I didn't feel good about it. And so I left UT Austin and went to UT Dallas, where I was also faculty of multiple departments, but I was research computing director and ran research computing there. And at UT Dallas, I started really focusing on reproducible computing. When I was running these big DOE simulations, we had jobs that ran for years. The biggest calculation we ran in 2012 used about 100 million CPU hours to run a single forward solve doing direct numerical simulation of Navier-Stokes. And so I really got into reproducibility, traceability, and started taking the tools of the public cloud and bringing them to research computing. We've been doing batch-based HPC since about 97, 98 in the National Science Foundation, and the way we use those systems haven't changed at all. We still pretty much use them the same way today. But between the time I started my PhD and now, there's this whole cloud industry, and they have some really nice tools. So I built a graduate program in reproducible computing and a postdoctoral program in facilitation. So I had an NSF-funded Workforce Development Center of Excellence, and I started creating these programs in research computing support, where I had postdocs with traditional PhDs who were brought into my research group, and I sort of taught them how to support and run large jobs using the tools of the public cloud. If you're familiar with the concept of DevOps, we did a lot of DevOps for science, and we'll talk about DevOps later today. 2022, I decided to flee the state of Texas. and I joined MIT, and I was the deputy executive director of the Massachusetts Green HPC Center. That's the supercomputing center for MIT, Harvard, Harvard Med, BU, Northeastern UMass system, and Yale as of last year. And I developed and built a bunch of shared services data center wide. And then about a year and a half ago, I joined Cambridge Computer as scientist in residence. And I actually have a really cool job. My job is spent, between 3 or 4 buckets of time. So first, I volunteer and run a lot of open source and open science projects. If you're familiar with OpenHPC, I run that project. OpenHPC is a Linux Foundation project, and it's the largest open source ecosystem to build supercomputers. OpenHPC was developed and run out of TAC, and TAC still uses OpenHPC. But OpenHPC runs the majority of the world's top 500 supercomputers, and it's the base stack that Dell, Lenovo, Intel, Huawei then use to build their commercial solutions. I also help and contribute and help run a project called the Open Storage Network, which we will talk about a little bit later today. Additionally, at Cambridge, I do our base job. I design and build HPC centers for science and AI. And then I get to travel and do events like this. So we have an annual budget from NVIDIA and from Dell, where I sort of travel around the country and developed custom curriculum for audiences like yours to sort of teach you the cool things I've done over the last couple of decades on reproducibility, but bring it to GPU computing and AI. So, we okay? Okay. So, what we're going to do in this first session is we're going to talk about reproducibility in AI and all the caveats and pitfalls with building these pipelines. And then I'm going to introduce you to some tools and some philosophy on how to organize your research life in order to make your science more reproducible, reliable, robust, etc. All right. Thank you very much. So let's talk about AI workflows in science. So scientific workflows and AI workflows share a lot of commonalities. There's going to be software that you develop, right? Everyone develops software these days. It could be just stitching a couple of codes together, right? Taking the output from one and the input of the other, or matplotlib and developing graphics and images to communicate our science. Those are all programming exercises, and hopefully you already version control everything. Version control is not something you do when you're done. Version control is something you do every step of the way. There's then software you consume, right? So my PhD in quantum mechanics, I did traditional software development, and I inherited a 1.5 million line Fortran 77 code. In fact, a lot of it was Fortran 7X. That is, it was written before the Fortran 77 standard was finalized. And all I needed was a Fortran compiler and BLAS libraries. And I was off and running with my code, right? Later on, we added some MPI-based parallelization, so I needed an MPI stack, but very few dependencies. Now, since I started my PhD to now, it's a lot harder to get a PhD, right? You might have seen some of these web comics go around, but every time one person gets a PhD in your field, the next person has to do a little more work, right? So the scope of projects you guys have to do are a lot bigger than we were doing 2 decades ago. And so, and oftentimes, a lot of the innovation comes at the intersection of fields, right, in this multidimensional space. So there are people who work with dozens, if not hundreds, of software packages written by other people, especially if you're in the data science field, right? There's a package for everything. And so we have to be able to manage this software. But here's the problem. Scientists don't get paid for software. Scientists get paid for science. And most of the software we consume are written by scientists. Consequently, most of the software that's written sucks, right? Especially in the Python ecosystem, right? I love Python, low barrier of entry, really easy to get going. I wish it was a little harder to publish a Python package. If you go around pip, right, or conda, there's some actual just disasters out there. And then this becomes a crucial part of your pipeline, but that package doesn't get updated, so you now have these very complicated dependencies. I need an older version of this and a newer version of that, and you try to run this in this unified environment, and it's very easy to create software stacks and workflows that by definition are not reproducible. All right? Then people are starting to develop workflows and more complicated pipelines. When I was working on my PhD, it was electronic structure theory. All I did was have an input file which specified the configuration of the molecule, right? Number of electrons, basis functions, et cetera. And then I ran a single executable, and my output was a single floating point number, the electronic energy. That's all I needed, right? You guys have these very complicated pipelines with lots of steps and a lot of stitching things together, and we tend to create these ad hoc workflows that are very fragile. Lastly, you're going to have data. Data you either acquire or data you consume, and we'll talk about that in the next talk this morning. So in academia, we typically run AI workloads on batch HPC systems. I would argue we need better alternatives. Batch HPC is great for prototyping, testing, tuning, post-training. But when you want to spin up an inferencing endpoint and run a service, you don't want to wait in the queue. And then most of your compute nodes are on an internal network that might not even be on the public internet, right? So we really need to do a better job of getting access to Kubernetes or other orchestrators that allow you to develop and deploy inferencing endpoints. All right, so we talked about all this crap up here and how life is hard, but in order to do science, we have to be able to reproduce our results, otherwise it's not science. We want to collaborate with people at disparate universities, right? Almost every large project these days, you have multiple PIs from multiple institutions, and you're not going to all get access to the same system, right? And we want to be able to scale and have governance and compliance. So this whole reproducibility thing, I would say conservatively, 99.9% of all papers published that involve computation are not reproducible. You don't know exactly what code they used or what version or what input file they used or what bits they twiddled, right, in order to make their solver converge, right? Or more importantly, what shared libraries were on the HPC system in lib64, right? They say you use this FFTW, but someone polluted lib64, right? And now you have an FFTW, you don't know what you're pointed to. So I ask you, are you really doing science? Probably not. So hopefully today we'll cover some tools that'll help you get there. All right. So my thesis statement, and something I've been working on for about a decade now, is bringing cloud native, declarative, and stateless concepts to batch HPC workloads solves most problems. So what are the problems with HPC systems? HPC workloads are inherently stateful. I SSH into a system. I submit a Slurm script, right? I don't know necessarily what's all installed on that compute node, and I don't know when things get updated and when things change. Or my Slurm script fails for some reason, so I change a local environmental variable in my running shell, resubmit. Did that metadata get captured? No. Cloud native paradigms help us express our full computational environment. Declarative approaches provide better portability and are less fragile than procedural. Procedural, turn that, move this, do this. That depends upon your state. Declarative techniques specify your end goal, and the tool analyzes the system and gets you to your end goal. The example I use when I explain this to my kids is, let's say I wanted my Alexa volume to be 5. And I apologize for anyone online if your Alexa just turned on. Well, if I know my Alexa is at volume 4, I just say, Alexa, turn up volume. But what if I don't know the state of my current Alexa volume? I can just say, Alexa, set volume 5. That's the difference between declarative and procedural. So I treat every single system as stateless in that when I want to run a workload, there's nothing on that system that I need to get started. It's all saved somewhere else, and somewhere else is in a Git repo. So managing software interactively with Conda and or pip probably isn't sufficient. Assume most people here have used Conda or pip or Python in some respects. Yeah. Well, the versions you get and the dependency chain depends upon what time and date you ran your command. And if you run it at a different point interactively, you're not necessarily going to get the same environment, and that can influence results. So let's review some of these and define them. So cloud native is not just things that run in the cloud. It's applications designed to run in a dynamic distributed environment on someone else's hardware where you embrace automation, scalability, and resilience. It's an architectural approach. It's a philosophy. Declarative is specify what you want, not how to achieve it. Examples are orchestrators in the cloud world, like Docker Compose or Kubernetes manifests, right? Today, we'll be talking about Conda environments and the environment.yaml file. That is a declarative specification. Stateless. Components don't retain data between requests. State is stored externally. And the most common example of stateless that makes sense is just SQL, databases, right? There's a remote system which has my data in some format I can query remotely. In any system I can pop open a shell and access that SQL system, I can do stateless computing. Well, we're going to use tools to do our HPC systems in this way. More importantly, any instance can handle the request, and it easily enables scaling and recovery of your jobs. And a good way to explain the cloud native paradigm is the concept of pets versus cattle. Pets have personality. They're beautiful, unique flowers. You go home, you pet them, you love them, you project your personality onto them, but they still have their own characteristics. Cattle sit there, all look mostly alike, and they just moo and eat grass, right? When I first started being in IT and running on my own servers, I loved my beautiful, unique flowers. I loved my pets. I'm a big Frank Zappa fan, so I named all my systems after his kids. So Moon Unit, Amit, Dweezil, and then machines that had something to do together, I would take songs and little tropes and name them after that. And my system made total sense to me, but it would be a disaster for anyone else. And every system was different because I set them up interactively. I installed stuff from different repos at different times, twiddled different bits, and every system was a little bit different. Cattle is what we want. Servers are numbered, not named, and everyone is identically configured using automation. When something breaks, if it's your pet, you take it to the hospital. If it's a cattle or a horse, you shoot it in the head and go do the workload somewhere else, right? That's what we're doing. Anything can break. When something breaks, you don't try to fix it. You terminate it and start over, right? Restart. So why does this matter for what we're doing? Well, how many of you have workstations in your lab or machines that you use independent of HPC because you can do things interactively, but if that machine goes down or someone's running on it, you now hit a bottleneck? You don't have to admit it to me. You can just admit it to yourself, right? It happens to everyone. Still to this day, I'll walk into computer labs and there'll be a bunch of desktops with a printer piece of paper taped to it that says running job, do not disturb, right? That's their queue system, right? Oftentimes you get these custom software builds that just work on one system, and you really get this, it works on my machine syndrome, especially in the Python world, Conda and pip world. And we have this fear of losing access to a particular system because if that system goes down, I can no longer finish my research. Cloud native, everything is defined in code. The same tooling you use on your laptop, the HPC, and the cloud. And you collaborate on science, not through sharing access to the same system. It's through sharing access to the same Git repo, which holds all your shared definitions for your work. You don't have to choose one or the other. Your computational infrastructure should be cattle. You should not be afraid to shoot them disposable, replaceable. Your data and your results, those are your pets. Those are the things you curate. Your software environments and tooling are going to be version controlled and declarative. So the practical steps are we define our environments declaratively, environment.yaml, Docker file. We store the definitions in version control. We build, rebuild on demand, and we test on multiple systems to ensure they're portable. Portable just means you're able to move from system to system, architecture to architecture, and sometimes operating system to operating system. The goal is to move from this node is special to this definition is reproducible. All right. So hopefully you already version control your software. More than just software can be tracked. My dot files are tracked. Every dot file I have is tracked. And when I log into a system, my bash RC checks my Git repo to see if anything's been updated and then asks me if I want to update them. So I keep my dot files in sync across all my systems. I wrote my own tool to do this like 2 decades ago. It's called dot splat because, dot splat as an asterisk. But there's many tools out there today. If you just Google dot file manager, you'll find a bunch of them. Majority of workflows consume third-party software. So how do we manage our software stacks? Historically, it was find someone else to do it. And HPC centers did this for a long time. And then you log onto the system and you do, module load GNU, module load OpenMPI, module load Trilinos or Petsy, or module load OpenFOAM, right? And when you're working in the traditional simulation world, this actually works pretty well, right? There's a limited number of codes. There's only a couple of them. Because they're developed by academics and they're these big sort of compiled language programs, they might change once a year, once every couple of years. But today, things are changing constantly. The PyTorch API has changed 3 times since I started this talk, right? So we need to find other ways of doing it. You could manually compile from source yourself. And for some tools, that's okay if it's from like the AutoConf or CMake world. If you've ever done /configure make check, make install, right? That's a build system. But really, we want to get away from those and into these declarative infrastructures that allow us to install stuff in user space. User space means you can run it as your user with non-escalated privileges. You can just use it yourself. And it's a package manager. These are basically app stores, except they're for the command line on HPC systems, and you don't need administrative access. So we're going to look at 3 approaches. We're going to look at Conda, SPAC, and containerization. So Conda. Conda is an open source package and environment manager for multiple programming languages. It was originally created for Python, and then R and Julia, sort of came onto play. But now almost anything is there. C, C++, Fortran, and some more obscure languages. Anaconda is a distribution of Conda. Do not use Anaconda. Couple of reasons. One, they changed their licensing to be not good. Let's just leave it at that. I don't want to get political. But find me at the happy hour, and I'd be happy to talk to you about Anaconda ad nauseum till you're sick, not me. Moreover, Anaconda is famous for DDoSing HPC or parallel file systems. Default Anaconda has like 310 plus packages installed in it. And when you instantiate your Anaconda environment, it has to source thousands of very small files. On a local disk, that's not bad, especially if it's an NVMe, like solid state drive, right? But on a parallel file system, you hit a metadata server, and then you point to all the data that's on different blocks, different locations. And you basically DDoS the metadata server. I had a Conda environment that would take 10 seconds to instantiate on my MacBook Pro, but on a large HPC parallel file system, it would take 10 minutes, right? And the HPC file system had orders of magnitude more bandwidth, right? All right. So the next step is maybe using Miniconda. Miniconda doesn't come with user packages. It's a bootstrap version that only includes Conda, Python, and the packages they depend upon. Things like zlib, right, for decompressing things, things like pip for installing things. Unfortunately, Conda is very slow at dependency resolution. And as your environments and your package dependencies get complicated, it can take tens of minutes, sometimes an hour more, just to figure out the dependency chain. So you can install Mamba. Mamba is a wrapper for Conda that performs the dependency resolution about 2 orders of magnitude faster, factor of 100. Then it calls Conda to install things. So if you want to stay in the Conda ecosystem using the Conda packages, start with mini Conda. I personally run MicroMamba. MicroMamba is a re-implementation as a single binary, and it does everything, and it's really set up for cloud native infrastructures. Is anyone familiar with CI/CD, continuous integration, continuous deployment? That's like when you check something into your Git repo, it spawns off a compute instance to run a test or check something. Well, that's what it's set up for, is that type of environment. It's inherently cloud native and stateless. So I tend to use MicroMamba. So you use Conda or Mamba, you can create isolated environments for your project. An environment is a set of packages that can be used in an environment together, but it's isolated from all the different versions. So with Conda, you can have 10 different versions of the same package installed, and then when you instantiate an environment, it'll load the one you need for that combination of packages. Right? There are 2 ways of creating a Conda environment. One is interactively, manual specification via the command line, and an environment file in YAML format. This is the one you want to do. This is stateful, right? All the things you typed in at your command line, when you type them in, and other things in your environment determine the output. This is a declarative file that guarantees reproducibility for a certain subset of the definition guarantees. Mostly works, 99+% of the time. There are some edge cases. So what is YAML? YAML stands for YAML ain't markup language, not yet another markup language. It's a YAML ain't markup language because it's not a markup language. It's a data serialization language. And this, of course, is another clever recursive acronym, which we have all over the open source space, right? GNU. GNU is not Unix, right? All right. YAML is human readable, and it's used for configuration files. It uses indentation, but it has to be spaces. Do not use tabs. It will not work with tabs. And it's common in DevOps, data science, and workflow tools. Why use YAML? Well, it's easy to read and edit by humans. It's easy to parse by tools, and it's version control friendly. If in your life you're choosing between 2 tools, and one has a text-based format, and one has a binary-based format, almost always choose the text-based if you're going to version control it, because your diffs are meaningful. Okay. So here's an example of a YAML file. So pound, right? That's our comment. Key : value. That's our string value. That's assigning the value of value to the keyword key. Number 42 is the syntax for doing a number. Any key, true or false, specifies as in a Boolean. You can do lists of items, so you can do key with multiple values. And you can do nested key value. Key value is a way you can set up things in YAML. All right. So Conda best practices. When starting a new environment, always generate the environment file rather than the command line. Maintain your YAML file in Git along with the code for doing the science, along with the scripts for submitting the code to do the science, along with the scripts for post-processing the results that generate the image that go in the publication to do the science. You version control your life. I'm a disaster in the real world. Digitally, I'm amazingly organized. And that's what lets me sleep at night. As you add package to the environment, update your environment file. Unless you must, try to avoid specifying the version of the file. This is where people really sometimes get them locked in a trap, where you specify explicit versions that work today, and then you come back in a couple of years and something has broken. And instead of getting every single API change for a package as it organically changes over time, you have to now backport hundreds of changes. And you get something that becomes very hard to maintain. Mixing conda and pip can cause issues. Avoid it if you can, but sometimes it's a must. If you're using conda as your tool, try to use conda first. If it's not in conda, then use pip. If you're using pip first, don't use conda. That's a good general philosophy. All right, SPAC. SPAC is the HPC package manager. It's open source, and it was developed out of the Department of Energy labs. If you ever heard of the Exascale Co-Design Project, ECP, it was a $20 billion 10-year program that built our big nation supercomputers and had a bunch of software developed. Things like Petsy and Trilinos are funded out of there. And SPAC was created as part of it. And SPAC really focuses on performant portability. That is, being able to determine the architecture and work with exotic interconnects, right? These new high-speed networks, or this new accelerator card, right? This FPGA. It's very flexible. And the SPAC team recently created the High Performance Software Foundation. It's a group of like-minded projects that are at the Linux Foundation. And SPAC does dependency management. It does versioning of your software as well as variants. So you could have a CPU version, a CUDA version, an AMD ROCm HIP version, a version for this weird processor that's experimental. It does environment isolation. It has huge platform support because the DOE has a lot of exotic hardware. And it's pretty extensible in that you can add things to it as well as add your own packages to it. The typical way you install SPAC is you pull down the repo with git clone, and then you source the configuration file. You find and install packages, load packages, or create and activate environments. And how it works looks very much like conda. It has a spac.yaml file, which works a lot like the environment.yaml file, and you version control that and use that very similarly. SPAC has a learning curve. It's much more complicated than the other tool we talked about, but it's extremely powerful and is the best performance portability tool for managing software. Containers. How many people are familiar with containers? Okay, so containers are a form of virtualization, except they just virtualize software. So you're familiar with like virtual machines, right? VirtualBox or something like that. That's where you virtualize the hardware and assign virtual CPUs and virtual network and virtual memory. And then you install a full operating system and kernel inside there, right? And that's its own dedicated environment. Well, containers run directly on your hardware, the bare metal hardware, or within a virtual machine. And it's an entire distribution. It's the entire software stack that's running as one executable. So if your application is inside the container, it only sees the environment inside the container. It doesn't see the system-wide lib64. It doesn't see the system-wide user include. If your sysadmin updates the system, it doesn't matter because your libraries and headers and everything you need are isolated in this container, right? And containers have several different runtimes. The first one was Docker, and Docker is fine to use on your personal laptops. but you're not going to use it on an HPC system. Docker requires a daemon, right, a process that runs, and it requires escalated privileges more often than not to run. And basically, the IAM model, the Identity and Access Management model, doesn't match to bare metal HPC. But there's really nice tooling called Docker Desktop, which you can just download and run on your Mac or your Windows machine. And Docker Desktop creates a traditional virtual machine with cores and memory, and then inside there runs the containers. But through the Mac command line or through Windows command line, you can invoke Docker containers directly. All right? Podman is a re-implementation of Docker that's full Libre gratis, open source. Docker has some limitations. Podman has no daemon, and it can run entirely in user space. The other nice thing about Podman is its syntax is exactly the same as Docker. So if you learn Docker and you go to an HPC system and you just do Podman instead of Docker, for 95+% of the things you're going to do, and it just works. And in fact, on a lot of systems, there's a convenience package installed called podman-docker, which is just system-wide alias docker equal podman. So you run docker run, and it's actually podman behind the scenes. Singularity is the HPC container. Singularity grew out of Lawrence Livermore National Labs, and eventually there was a schism in the project. There was argument over the direction. So now there's Singularity CE, the community edition, and Apptainer. Apptainer is the one that's maintained by a company named CIQ, and CIQ is the company that also creates and maintains Rocky Linux, and they're the original team that creates CentOS, decades ago, before IBM and Red Hat bought them out and then killed it, right? Treated it like cattle. So I like to support the CIQ folks. I think they're good for the community. So I run Apptainer, but they're exactly the same in how you use them. So with containers, there's multiple ways to build them, but Docker files are the most robust and have the most examples. And a Docker file can be used to build a Docker container, a Podman container, or a Singularity/Apptainer container. So I use Docker files as my base for building containers. Each instruction in a Docker file specifies a step-by-step process of creating the image. Some of it looks declarative, and some of it looks procedural in how it works. However, you're always starting from a tabula rasa, right? A clean slate. So it is reproducible by definition. So you can use Docker and Podman and Singularity containers. And one neat trick is to use Conda, but in a Docker container, right? Or a container in general, right? Remember when we set up these Conda environments, you're still on the bare metal system. So if let's say FFTW wasn't installed in the system-wide, and you installed a Conda package that required FFTW, it's going to install that version of FFTW for you. But let's say later, a sysadmin installs the system-wide FFTW. Well, the next time you run it, it kind of depends upon what your environmental variables are and the order of your include and LD library paths into what happens. And that scares me. So if you do it inside of a Docker file, you control all the shared libs and include files. And SPAC has tooling to go from a spac.yaml file directly into a container, which is nice as well. Here's some really cool stuff. So containers have something called a container registry, right? Have you ever used like Docker Hub or NVIDIA Cloud and things like that? And that's a whole new set of tooling and ways you interact with it. And that's another place where your data is stored. So there's an entire ecosystem of tools that allow you to take your Git repo and turn that into a Docker registry. So your Docker file lives along with your Conda files and your SPAC files and your science, right? Very cool. So repo to Docker is an open source tool that automates the process of creating Docker images from your Git repos. Because it's in a Git repo, it's by definition reproducibility, has traceability, right? Has all your provenance, and you can share it and collaborate and branch and fork and merge and pull and do all those cool things. So repo to Docker inspects the contents of a repository to determine the dependencies and then builds the container for you. There's also a repo to Podman and a repo to Apptainer. So I can go to any system and type repo to Apptainer, github.com/my username/my Git repo, and that will build my reproducible container pipeline. Really cool stuff. Then there's something called the Binder project. The Binder project has examples for all the things we're going to talk about today, where you can just fork the and edit a requirements.txt for pip or an environment.yaml for conda. And then your Docker container is ready to be built, and you've got your reproducible environment in 2 steps. Then there's something called Binder Hub. Is everyone familiar with Jupyter Hub? So Binder Hub is a splash page for Jupyter Hub where you can paste in the URL for your Git repo, and that'll build your environment and launch your Jupyter Notebook for you. So here's examples. And so all my slide decks have links at the end. You'll get a copy of the slides, and you'll be able to go and find all this. You don't have to write any of this down. So here's an example of a Julia repo, or a pip repo, or an Octave repo, R Conda, Conda, Julia Python, Jupyter Hub, pip file, etc. And you just fork those and get started. Here's an example of what a Binder Hub looks like. So there's a community, there's community resources of Binder that are out there that anyone can use. I help maintain some of these for the community in my spare time. But these have very limited resources, and they're often oversubscribed, and they don't have GPUs. But you can deploy this on your own resources with GPUs and have that kind of. So all I have to do is paste in my URL, launch, and that'll build the container and launch my environment. So here's an example of one of my GitHub repos that is a Binder Hub repo. And then on my readme.md, I have this button I can click, and that will automatically build my container on the Binder Hub instance that I specified for, and then launch Jupyter Hub and do all the cool things I asked it to do. And I'm not going to do that interactively because that's going to take a while. But here's some of the things you can add. So this is an Ubuntu-based image. So here are packages I can add if I need system packages. Here's my Conda environment where I can just add packages. Next time I build the container, it'll update it. And here's a post-build script where I set some like S3 bucket information in my bash RC. I change colors because I have opinions. I pull down a tarball from my GitHub repo and extract it. And these are like my coursework. These are example scripts and homeworks and exercises. And then I pull down the Git repo, and I now have my full environment ready to go. So let's click that, let that run, and then I'll go back to the slideshow. And I'll check back on it a little bit. Now, Binder Hub requires Kubernetes, and most campuses do not have Kubernetes or don't support it on-prem. There are other ways to get access to it. So there's a national project called NRP, the National Research Platform. It's run by SDSC, and you buy hardware, and they'll install and run Kubernetes on it for you in your own data center. In exchange, you donate a portion of the hardware back to the community to let other people run on your stuff, but they run Kubernetes for you, and you can buy some GPUs and run Binder Hub. Or you can get access to Jetstream 2. How many people know what Access is, the NSF Access program? So it's access-ci.org. Any eligible researcher, which doesn't even require NSF funding, can get access to free national resources, and that's how you get access to TAC or San Diego Supercomputing Center or Open Storage Network for my S3 as a service, for our S3 as a service infrastructure. Well, Jetstream 2 is a joint effort run by University of Indiana and TAC, and it's OpenStack as a service. OpenStack is Red Hat's virtualization. And there's ways and recipes through Jetstream 2 where you can deploy your own binder hub and actually federate it with your Minnesota, credentials and do authentication that way. So really cool stuff. Repo to Docker, repo to Apptainer, they're the perfect coursework tools because things just work. And it worked. So here is my Jupyter notebook that's been loaded that has all my Git repos, my exercises, my assignments. And this is reproducible by design. So imagine all your bioimaging pipelines were set up like this, right? Your BAM tools, right? Your complex CFD codes. You click a button and you get your environment. That's really cool. New graduate students often take months to get their software stack set up and curated on their laptop before they can do research. And then once they outgrow their laptop, they now have to do it again on another system, right? This stuff saves time. I know it seems time consuming. And I know, how do I turn this off? Oh, there it is, more. Okay. I get a lot of pushback when I proselytize, right? When I preach my philosophy on how to do things. Because a lot of it is religion. And people say, Chris, I just don't have time to do this. I realize it'll save me time eventually, but I got to get this paper out. I have this deadline. I've got to graduate, right? The tipping point or the crossing point is not nearly as far along the time domain as you think. And very soon, this saves you time instead of costing you more time, right? You've heard sort of the myth of the 10x engineer, right? And they're 10 times more productive. Screw that. I'm 100 to 1,000 times more productive than most people doing HPC because I do everything this way. The first time I do something, it's a beautiful, unique flower. The second time I do it, I automate it. And I have thousands of tools that I've automated this way over the last 20 some odd years. And so I just have a Swiss Army knife that's huge, right, for solving any problem. All right, so let's go through some examples. And so I'm going to go through examples with Conda, SPAC, and containers using PyTorch. PyTorch is one of these enabling technologies that almost everyone uses these days, and it's still kind of fragile, and it's still kind of hard to get up and running. PyTorch requires specific CUDA versions, and the CUDA runtime must match the system drivers. And more often than not, the people in this room do not influence what the system drivers are. That's the sysadmins, unless you're running on a virtual environment or a cloud environment. So the goal is to create reproducible, portable GPU computing. So Conda, great way to go. Cross-platform, cross-language, handles complex dependencies. It's good for rapid prototyping. It's good for local development. It's good for small projects. But if I'm doing something substantial and running like multi-node jobs, I would use a different tool. SPAC, HPC optimized build. You build from source with system-specific optimizations. And this is best for performance-critical HPC applications. Apptainer and Singularity, complete environment isolation. Both SPAC and Conda have ways for system files or system libraries to bleed or leak into your environment. Containerization, it cannot happen. So if you like Conda or you like SPAC, you can integrate them with a container. Now, CUDA version compatibility. System driver determines the maximum CUDA version. your container or your environment must have a CUDA version less than or equal to the driver version. And if you run NVIDIA-SMI and grep for CUDA version, you'll see it. It's in the top right of that NVIDIA SMI. All right. So let's look at what a PyTorch for Combo Mamba would look like. So channels are the location of the repos. And remember when I told you Anaconda was problematic because of licensing changes? The default Conda repos are actually problematic as well. If you notice on my channel, I do not have default. Default are the ones that have licensing restrictions depending on what you do with your work. So you can use mini Conda, though I recommend micro Mamba, but do not use the Conda channel. They haven't done it yet. Well, they've started doing it. They're basically license trolls, right? If you're familiar with this, they changed the open source license, and then Anaconda reached out to like MIT, and they're like, you owe us $1 million for all the people from MIT who are hitting it. And that's $1 million a year, right? They're going after people. So don't use the default. So I'm using PyTorch, so I'm going to use PyTorch as my first channel. I'm using CUDA, so I'm going to use NVIDIA as my second channel. And then Conda Forge is the Wild West. Conda Forge is where everyone publishes packages that's a scientist. So you put that last. You only pull a package that another scientist builds if that's the only way to get it. Because it'll pull from those in order. So it'll find PyTorch from PyTorch. And then it'll hit CUDA. It won't see it in PyTorch, but it'll get it from NVIDIA, etc. Notice I only specified the version of 2 packages. I did not specify my Python, my Torch Audio, my NumPy, my Jupyter, or my Matplotlib. The only thing I specified was my CUDA, because my system was running something like 12, say my system's running 12.8. I could hard code 12.8, but I'd rather just put 12 and get the latest version. And as the driver of the system gets updated, I automatically get the newest version. If I build it and it builds too new of a version, you'll get an error, and you know you have to up your hard coding from major to minor, and then maybe minor to micro. But you start with the least restrictive as possible. And then, common problem is people specify PyTorch, you need PyTorch CUDA for the GPU version. All right, so Conda env create to my file. Conda activate instantiates my environment. I now have my isolated Conda environment I can do PyTorch stuff with. And if you're using Mamba, you just replace Conda with Mamba, and that's faster resolving. Common troubleshooting problems. If you get CUDA available false, well, check, make sure PyTorch CUDA was installed and not just PyTorch. Verify the channel priority. PyTorch should be first. Ensure your CUDA version is less than or equal to the driver version. If you have a libqdart.so.11.0 cannot open shared object, most of the people who've used CUDA has probably seen this error before. That's because there's a mismatch between your version and the system version. And if it's really slow, use Mamba. SPAC. SPAC uses a YAML file. It looks very similar to the way Conda does it, except instead of equal signs, it uses @ signs for versions, and it uses plus for variants. So in the CUDA world, it was PyTorch versus PyTorch-CUDA, right? Here, it's PyTorch @version plus CUDA. CUDA is a variant that gives you the CUDA enabled. And then for here, I specified CUDA_arch equals 80. That is the architecture optimizations for an A100 GPU. I was on an Ampere node. I had an A100 GPU, so I coded, so I optimized it for that architecture. And it's things like this which make SPAC more performant. And then view true and concretizer unify equal true. just set those unless you're really advanced and you know why you don't. But view equals true, populate your packages with symlinks so they appear as a unified package archive in a directory. Concretizer unify true tries to use the least common denominator version of packages that are dependencies for multiple packages. Without unify equal true, this package will say it prefers version 2 of package blah, where this one runs version 3 of package blah, and it'll install both. So, looks very similar. Spac env create, PyTorch GPU, spac.yaml, spac env activate. I then concretize, which resolves package specs into an install recipe, and then spac install. Now, spac install does have binary caches like apt or conda or whatever. However, there's a lot more variables with spac. It's down to the operating system, the kernel, what version of the operating system, what AMD or Intel processor you're using, what version of CUDA you're using. And all those linear combinations mean that often there won't be a current binary cached. So this will compile if need. And last I ran this, it took 2 hours to build from source because it builds everything from scratch. All right. So let's talk about ways to do it with container. So the nice thing about container is that there's container registries that are public. And if your container is already out there in the real world, you can just pull it down and use it. So NVIDIA has a catalog of containers at NGC, and NGC stands for NVIDIA GPU Cloud or NVIDIA GPU Containers, depending on what context. And they always call it NVIDIA NGC, so it's NVIDIA GPU Cloud. But you can visit the catalog and see the list of the versions. Here I'm pulling version 2407, so that was from 2024 July, right? So I pull it down, and then I build it into a CIF file. And a CIF file is a binary that's a container. And if I just run the container, like /pytorch.cif, if it's executable, it'll run the container. Method 2, start with an official container. Here I'm starting with CUDA 11.8 on an Ubuntu system. And then inside that container, when the container that gets built, I install Miniconda, I clean it up, I accept their onerous terms of service, I copy that environment.yaml that we created previously into the container, I build my Conda environment into the container, I set my default directory when I instantiate the container to workspace, and then when I instantiate the container, it automatically activates my PyTorch GPU. This is pretty cool. So this is the best of both worlds. All right. Any questions on software installation, containers, anything? Yeah, let's get some questions.
Yeah, this is great. Question about non-environment.
Mm-hmm. So you want to talk about how that works, right? Is that? Mm-hmm.
What I noticed is that they tend to be very specific versions. Is there a way to turn that off?
Yeah, so when you build your Conda environment interactively, and then write an environment.yaml file, it's going to write out the exact versions that are installed. So you delete those. Yeah, just delete the versions. So that was a very good question from the audience. First, he said, my talk was great. So the people online, you need to make sure you hear that. And he asked about the concept of stateless Conda, and when he installs a Conda environment manually from the command line, and then exports the environment.yaml file, it has versions hard-coded. Okay, so let's talk about why you want environment.yaml files and when you want them for what purpose. So if I'm building an environment to run my science, in my Slurm script, it builds my Conda environment. And when my Slurm script is done, it deletes my Conda environment. So that every time I run my job, it regenerates from scratch. And if it fails, I know the first time a single version has changed and I need to make one API update. Okay. When my calculation is done in my Slurm script, I also write out the environment.yaml file with all the versions in it. And then I check in that specific YAML file for that single Slurm job with environment.yaml.slurmjobid into my GitHub along with my results. So I build from one that's not specified, so I always get the latest environment. But when I write out my results, I generate another one that's with the specific versions, so I can always generate that exact environment when needed. And in fact, since my output files are mostly text files in the quantum chemistry world, I also write the environment.yaml with version numbers at the end of the output file. Because sometimes your world will blow up and your output files will get divorced from your input files and your other stuff, and you'll find an output file and you're like, that's the result I need to graduate. How the hell did I create that? And that output file is the environment I need to regenerate. And in fact, when I generate images, in the metadata of the image, I write all the information about the packages that were used to create that, right? Does that answer your question? Cool. Other questions? We got some online? Am I supposed to read them? Let's see here. Yeah, I can't read that. I need new glasses. Fantastic.
Going through the analysis software, so that they can tell which modules and the versions operated on. And in particular, data information as to the data source at annual introduction events where a researcher has to apply and document their heuristics, if any, to refine data before staging it to next pipeline.
Can you come to the happy hour? That's a pretty involved question. I am pretty time constrained. What I would say is send me an email. My email's at the beginning of this. It's going to be on every slide deck. Send me an email, and I'll have someone set up a meeting for us to talk about this, because that's a really good question. And then based upon what comes out of that, I'll send the answer to Laura, and you can circulate it. Question in the crowd? Yes.
Sometimes when you use single versions, try to create that environment, you get a much better.
That is because that environment was first created a year ago, and now you're joining an environment with all the versions, and the repositories have cleaned up or changed their dependency chain, and Conda is somewhat non-deterministic in terms of how it does its solver, especially if you haven't updated in a long time, or your channel order is the same, but a package previously wasn't in a channel, and now it's in a channel that's before the one it was installed before. So that's why you really need to build and test often. And that's why Conda I kind of have a love-hate relationship with. And it's exacerbated because scientists can't write software for the most part, right? But does that help answer your question, Thomas? Well, that's why containers have a greater advantage if you use a container registry or if you generate a CIF file. So these CIF files, these Singularity Apptainer images, are binaries that have your entire container in it at runtime. And the example I said where I would generate an environment.yaml.slurmjobid, I actually generate a container.cif.jobid, and I put that container into an S3 bucket so I can run that job again later. But it's an imperfect solution, but we live in an imperfect world. But it's better than what we typically do. Yes? Mhm. Mhm. Yeah. So that's a good question. What I do is I run an MD5 sum on my container, and then I have a system of symlinks. So that, or you can't really do symlinks in an S3 bucket. I have a manifest file. The devil is always in the details, and I have to decide at what level to discuss. But great question. The question is, do I do that for every single Singularity container if I run 1,000 jobs per day? No. You only need to do it when you update the container. So I tend to submit a job and it runs for a week or two. So I have fewer containers. With you, what you'll actually want to do is use a workflow engine tool like Nextflow or SnakeMake, which is the topic of the next lecture. So why don't we go ahead and take a break now? I have about 10 more minutes of content on this and then the data talk, but that should end up timing just about right. So let's go ahead and take our break now, and we'll resume at 11:30. Thank you very much. So we had a couple of questions online. The first question about manual intervention and heuristics, and if I change or twiddle a bit, how do I capture the metadata? That's the one you read earlier. That's very pipeline specific, and the philosophy how you would do it would be tool specific. So please, 100% reach out to me via email. I'd be happy to set up a meeting to talk to you about it. There was a question about managing data, and is there something better than Git blob? Yes, that's the subject of this talk. Once I finish up the workflow stuff, we're going to talk about GitOps and DataOps for reproducibility in the data space. And then there was a question about Mathematica versus Jupyter, and how you can open a Mathematica notebook from 20 years ago and it works, but a Jupyter notebook doesn't necessarily work. Well, I'm not entirely familiar with Mathematica. I haven't used it very much. I only use Libre and Gratis software. I only use open source, open science stuff because I don't trust other people. And I do a lot of work on numerical methods, and I need to understand convergence, and I need to see what's in the code. But Mathematica is one company, one monolith who has one unified vision, and they can dictate their API and how things change and backwards compatibility. Where a Jupyter notebook could be one package from one developer, or it could be 100 packages from 1,000 different developers, and you don't know the last time one of them was updated. So it's just open science and a world of volunteers contributing versus one monolithic corporation, right? So it's really hard to compare. All right, so we had a question earlier about, do I check in my Singularity CIF file for all 1,000 jobs I run a day? No, right? And there's specific tooling that's set up to help for you. So you mentioned you're running 1,000 jobs per day, and at some point, if you're still doing them interactively, you're probably doing like Slurm job arrays or something, but you might be manually submitting them, or you create some clever bash scripts and you start automating things, right? So here's an example of a quick bash script, for I in 5, do this thing 5 times, and the script crashes at sample C, and if I rerun it, it starts back over. And of course, it's simple to edit this example, but if you extend this to huge pipelines, they become fragile. If I change an input file for one of my steps, it reprocesses everything. If I run 1,000 samples, at least this example, there's no parallelization. It runs serially. 6 months later, I don't necessarily remember what parameters I twiddled, and you often get this, it works on my machine, problem that we talked about earlier. Where's my remote? I lose my remote. There it is. All right. So what's a workflow management system? A workflow management system is something that provides dependency tracking. It automatically determines what needs to be rerun. It only processes changed inputs. So if I change the input file in step C, it'll only rerun step C. It tracks relationship between files and inputs and outputs. Workflow engines are nothing more than input-output maps. That's all they are. It does automatic parallelization. It identifies independent tasks and run them concurrently. It could run them on multi-core if you're running on a single like SMP system. It could run on a cluster, it could run in the cloud, and it maximizes resource utilization. And it brings reproducibility because you have a declarative specification of your pipeline. It's a text file, which you version control. And it captures provenance, how every output was created. They're portable. The same pipeline should run interactively on your laptop, but when you run it on an HPC system, you tell it it's Slurm or PBS or LSF or SunGrid engine, and it automatically converts your workflow to that workflow engine. There's no hard-coded paths or assumptions. And it has resume checkpoint capabilities at the per task level, right? Where the pipeline stops at step 47, well, instead of rerunning from scratch and putting a breakpoint, you just say, slip me into my pipeline at step 47 and let's interactively debug. It saves time, compute resources, and this is debatable. My mental health is not great, but it's probably better than if I didn't use workflow tools. Each task in a workflow system is isolated in a directory with logs. And the complete command line is captured in a file. Inputs and outputs are tracked. Provenance trail from data to results. So here's an example of a Nextflow workflow where it created these subdirectories automatically. And for this hash job ID, here is the dot file. So if I just do an ls, I don't see it. But if I do an ls-a, I see the command line I ran. I see standard output and standard error merged. I see standard error only. I see when the job started, when it exited, and there's always a symlink to something called input_file to where the original input file was. So we're going to go through two examples. Nextflow is a very popular tool, specifically in the genomics and bioinformatics world. For the person with 1,000 examples, are you doing computational biology? Okay. I guess everything could technically be computational biology, right? So Nextflow is in a domain-specific language that's based on Groovy and Java. Groovy runs on the JVM, the Java Virtual Machine, and it has features of Java, Ruby, and Smalltalk for those who like esoteric programming languages. And it's a data flow programming model. It has native support for Docker and Singularity Apptainer. It has support for Slurm, SGE, PBS, HPC schedulers. And if you give it your AWS or GCP or Azure credentials, it'll dynamically spawn virtual machine instances or AWS parallel cluster jobs, submit your jobs, run them, and then spin down those resources. It has resume capabilities to pick out where you left off, and it has a large community curated collection of pipelines. Snakebake is the one I prefer because, one, I don't like Java, and I don't like learning domain-specific languages for one task. Snakebake is Python-based. It's a rule-based workflow. It's a rule parallel, where Nextflow is a data parallel paradigm. I tend to think more in task-based than data flow-based. It has native Conda integration, automatic dependency resolution, supports our containers, and it's really popular in data science as well as bioinformatics. It has rules to describe how to create output files from input files. Again, it's just a fancy way of doing an input-output map. And Snakebake figures out execution order automatically. Basically, it creates a DAG, a directed acyclic graph, to know how to traverse the workflow. If you've ever written a makefile, that's what inspired Snakebake. And I've written a lot of makefiles. That's another reason why I use Snakebake. So let's kind of bring this all together. This is my Git repo for my reproducible science project. I have my project directory, my .git is my Git repo. I have a Conda environment. I have a Docker file that uses the environment.yaml to build my container. Maybe I have some SPAC where I need some compiled packages or libraries that I want to optimize for my architecture to call from my Conda. I either have a Nextflow or a Snakebake workflow definition. I then have my analysis scripts, right? I then have a data directory and a results directory, and then a README file. Now you notice in this data and results directory, they're empty, and I have a .getKeep. That means keep the directory and check the directory in, but there's not going to be anything in there. Or there's a getIgnore in there. And that's where we tie in the data component and how we manage data in the same unified view as our Git repo, but we're not checking in our gigabytes of files of binaries into GitHub. Bringing this all together, git add environment.yaml, Docker file, and my snakemake. I commit my reproducible environment. I run my great science. I get that final result that makes my PI sign off and lets me graduate. I then tag this in Git. And now I can always pull down a specific historical version of Git and reproduce your life. It's an amazingly powerful paradigm. All right. So that segues into the next talk. All right. So we've talked about how to track our software we develop, the software we consume of others, the runtimes, the workflows, the data processing, but what about the data? Unless you're working with like CSV files that are modest size, you're not going to keep your data in your Git repo. So what do? Well, you've heard this opinionated statement before, but let's add a couple of more caveats to that. Treating every system as stateless ensures portability not only in terms of software, conda spec, OS and libraries, container, workflow tools, but also in terms of data. Simply leaving data on a POSIX file system for AI workloads probably isn't sufficient. POSIX is just an interactive file system on a Unix system, LSCD, et cetera. That's a POSIX file system. Now, science is all about reproducibility, right? And I'm not an AI person, right? I'm a simulation, first principles, quantum guy. And when I see a result, there's certain physical realities that should adhere. My pressures and temperatures should be positive in Kelvin, right? I know for a hypersonic, for a hypersonic flow, what my velocity should be. I kind of know physically what should happen. So if I see something wrong, I have a gut intuition, right? AI is just interpolation. AI has no fundamental truths about what the answer should be, especially in generative AI, right? And so if you have a result that you don't understand why you got it, either positive or negative, and your data is just on a POSIX file system, could you regenerate that LLM query or that tuned model? Well, data that sits on a POSIX file system is live data. And I used to do system support, do IT ticket support while I was working on my PhD. And dozens of times I get a ticket that says, Chris, my lamps or my Gromax no longer runs. I did not change my input file. What did you break? You go to their input file, at the very end you see :WQ, because they were in the wrong Vim mode. And instead of exiting, they added a little WQ turd to the end of their file. And these old Fortran 77 code are fixed input file formats. So their code broke. They know that broke. Now imagine the data that you need to regenerate a model. It sits on that live file system, and Graham gets mad at you and adds a little sabotage to it, right? Or one of your group mates. You have a shared group, right, directory that is group readable and writable. Well, POSIX file systems have no observability, no hysteresis, no way for you to understand the life cycle of that data. So we're going to look at tools from the cloud native world to build stateless data pipelines to go along with the philosophy from the first talk. And the inspiration I took for this is from the concept of DevOps. So we talked about the concept of pets versus cattle. DevOps are the set of tools which herd and feed the cattle. DevOps is the philosophy of treating operations, that is IT management of a system, as a software development process. So you have code, and you have declarative syntax, and you version control, not your software, but the definitions that build your operating system, that build your systems. That's the concept of DevOps. Now, the important part of DevOps is the dev part. But marketing people are evil. And so anything that applies the concept of DevOps to some new concept is known as splat ops and not dev splat. So if I treat Git as my single source of truth, it's called GitOps. If I treat data as something that's represented in code and I can programmatically interact with that, that's called DataOps. And it should be, well, dev Git just doesn't sound good. But data dev, dev data, that doesn't sound good either. So maybe marketing people are pretty smart after all. But I just think it's funny. You know, the only way or only area where I refer to it as dev splat as opposed to splat ops is documentation as code. That's usually called dev docs, because doc ops sounds a little weird too. So, but anytime you see dev or ops, it's usually bringing the concept of software development to somewhere else. And there are the concept of ML ops and LLM ops, which are automating the full pipeline of the tuning and the training and the inference. Now, a great place to start with aggregating your data is to use S3. S3 is an API to access storage over HTTPS and HTTP, but don't use HTTP. HTTPS is the same protocol that web browsers run, right, with SSL or TLS, you know, SSL wrapped in TLS. And so on any system where you can outbound hit the public internet, you can programmatically interact with your data. So I tend to use S3 endpoints as my organizing principle for my data. Also, S3 storage lives outside of institutional IAM boundaries. Let's say, you know, scientists are collaborating on a project together at multiple institutions. Well, they all, you know, all the other institutions collaborating with you guys would need to get credentials on your campus system, and then get your VPN, and then SSH into your HPC system, and then there's a shared directory. Do scientists do that? No. And so historically, it's data sharing across institutional boundaries, which created shadow IT. And shadow IT is stuff you as users do that's outside of the IT organization to get around policies. And so that's how things like Dropbox became popular, right? Or Google Drive. And of course, when you start doing shadow IT, you often become victims of the whims of capitalists, right? Google Drive offered all scientists unlimited storage for about a decade. And then a couple of years ago, they're like, hey, you guys have 5 petabytes here. We're changing our free tier to 10 gigabytes instead of unlimited. And so a lot of what I did before I came to Cambridge Computer when I was at MGH-PCC is we helped people migrate data out of GCP into another system. And a certain university that I worked with found out they had 5 petabytes in GCP, and it took them a year to get out. And they were paying several $100,000 a month just to transfer the data out. So shadow IT solves a problem right now and creates new problems in the future, and you don't know how far along in the time domain that is. S3 doesn't use traditional username and passwords. It uses API keys. So you guys can create an S3 bucket and then share the credentials with your collaborators around the world, and they can interact with that. So I talked about in the software section and workflow sections how you don't share compute resources, you share definitions, but you do share data. Another way of thinking about it is you share pets, but you don't share cattle. Cool? All right. Now, There's several different ways for you as scientists to get access to S3 storage. One is Open Storage Network. Open Storage Network is a volunteer project that I work on along with MGH-PCC, San Diego, NCSA, Johns Hopkins, and RINCE, the Research Triangle folks at Chapel Hill. And we provide this as a service to the nation. We currently have 17 data centers we're in, where we provide a little bit over 50 petabytes to the community. The majority of that is hardware purchased by a university. So Charles Wynn, if you know him, he has an OSN pod. He's in CSE. And the way OSN works is any organization that's a EDU, a government lab, or a nonprofit can buy an OSN pod. It's $120,000 today. It gets delivered to your data center. You rack and stack it. And then you send our team $10,000 a year, and we run it for you. For that $120K, you get 1.2 petabytes of self-service S3 storage. That is, there's a web portal where you can log in with your Minnesota credentials, request a bucket, we deploy it, and then you can add users around the world and they can get access to the storage. We require you donate 20% of that storage to the nation. And so 20% of that storage that we get back for running it for you goes to the access program. So any access eligible PI can get up to 50 terabytes on OSN for free per project. So Charles owns an OSN pod. You want to use that one because it's close, but Charles is using it for other things. Well, go to Access CI, ask for 50 terabytes, and then tell it you want on the Minnesota pod. And we'll give you storage on your pod that comes from Access instead of internal. So there's 300 terabytes up for grabs for anyone who wants to have it to play with this stuff. We are going to be trying to build this out, but it's a volunteer effort. And the NSF was supposed to talk to us about funding, continuing funding, but apparently the government shut down right now. So we'll have to figure that out at some point. But OSN's not the only place you can get S3. So I talked about the National Research Platform and Kubernetes as a service. Their system is actually called Nautilus. They call it potluck computing. I like to think of it as stone supercomputing, if you're familiar with that parable. But you bring your hardware and it all becomes part of a shared capacity. That has S3 resources. There's currently the National AI Resource, what is it? Research Resource something, pilot. It's an NSF-funded effort where there's tons of resources donated to NSF researchers, including GCP, Azure, AWS, and you can get S3 buckets from there. You can pay for it. It's kind of expensive. The standard tier of AWS, if you're paying for it, is about $270 per terabyte year. Dropbox is about $100 per terabyte year. There are other services. Wasabi is, I think, $60 per terabyte year for their S3 as a service. Backblaze B2 is about the same price. There's also POSIX gateways. So if you have a standard file system, you can install a software shim that exposes an S3 endpoint that you use like S3, but it writes to your local file system. Lastly, a lot of commercial file systems have an S3 endpoint. Like you guys have VAST as your storage appliance. VAST presents storage. I think you have a VAST, right? Oh, so you guys have Ceph. There you go. Okay, so you guys have an open source. So OSN is built on Ceph, which is Red Hat's open source object store. And so Graham has an S3 service. Great, fantastic. I'll be quiet now. All right, GitOps. GitOps is an operational framework that uses Git as the single source of truth. And what we were talking about in the first talk is basically GitOps. Now we're bringing data that. Git is the single source of truth. Use declarative tools. Version control provides your audible history and a way to roll back and reproduce and capture all the metadata. I then integrate it with CI/CD. That is, GitHub has something called GitHub Actions, and you can specify a workflow that when something is checked into GitHub, it automatically triggers an event. So when I check in my environment.yaml file to GitHub, it automatically spins up a GitHub runner and tries to build the environment. And if it fails, I can either do a git blame, and that'll yell at me for doing it, Or I can do it as a pre-commit hook and reject the check-in and say, lol, no, that broke, right? Try again. So there's many ways to do this. Any open source project can get access to a large number of free GitHub runner hours, but you can also host your own GitHub runners on your own hardware, and they don't need inbound access. So you can install a GitHub Actions runner on an HPC system or on a node, and then periodically it'll ping GitHub and say, do you have anything in your queue? And that'll run your workflows automatically on your own hardware. And in fact, my graduate students, when I used to have some, they were not allowed to submit jobs to an HPC system interactively. They could only check things into GitHub, which would trigger a Slurm job submission. If I gate Slurm behind Git, then by definition, I've captured all the metadata to regenerate that workflow. And the students at UT Dallas and other organizations I've worked who use this methodology when they weren't my students got higher priority on the Slurm system. I saw Graham peek up. He's like, no, don't do that. All right. The goal is to treat deployments as immutable. That is, if I pull down and run something and it doesn't work, I don't twiddle the bits at the command line and retry. I make the changes, check them in, and try again. Now, storing data in Git directly is a path to pain for large files. Git has something called LFS built in, which is large file support, which separates out files that are tagged as Git LFS and sends them to a different storage location than your Git repo, but you use the same tooling and the same checkout directory to interact with it. And that's the answer to the question online about the difference between Git blobs. Git LFS is where you want to start. Git LFS is an extension to Git that replaces large text files with pointers that say this data is not in the Git repo, the pointer is, and it points to the data that's in an S3 bucket or on another file system somewhere. GitHub and GitLab support Git LFS out of the box. GitHub only gives you free LFS up to 10 megs. And then after that, it is ridiculously expensive. We're talking thousands of dollars per terabyte year. GitLab can be self-hosted on-prem, in the cloud, or Nautilus and NRP. They have GitLab as a service that you can sign up and use. And you can point GitLab's LFS at an S3 bucket, such as one on OSN. If you're not using GitHub or GitLab's LFS service, and you want to use GitHub, but use another S3 bucket for Git LFS, you can do that. However, it's not serverless. So on your local machine where you're running these git add, git check-in, git LFS, you run an npm proxy. There's basically a server that runs on your local machine, and your git LFS goes to the proxy, and then that sends it to the S3 bucket. And the proxy is on your local machine. So you can spin up this proxy wherever you need, on an HPC login node, on a compute node, etc. From there, you simply do git LFS track path to file. Here I've done globbing, where I'm now using Git LFS to track all my HDF5 files instead of checking those into GitHub directory. And once you've added it to Git LFS, it's no longer going to check it into your repository. It's going to diff it and check versions into a different location. So that's the GitOps approach. DataOps is a data management practice that leverages tools that allow you to programmatically interact on the data. So in the GitOps approach, we're just checking in, checking out, right? We're just moving data in and out, but we're not interacting with it programmatically. DataOps allow you to have a more powerful way to slice and interact with your data. Key principles: collaboration, right? We can exchange data. Automation, it's easy to make repeatable. Quality and governance, scalability, monitoring and observability. You know what happened to your data at all times, right? In the POSIX paradigm, I add these little :WQs, and I have no idea when it got there by whom. Here, every single change to my file, I know who, what, when, where, and why. Very powerful paradigms. Compared to GitOps, the tools of DataOps are more powerful, but require more workflow and or code changes. I'm going to talk about DVC and LakeFS, are two open source tools that I think pretty adequately explain the space. So DVC stands for Data Version Control. So DVC is an open source version control designed for managing machine learning models, data sets, and other data assets. It is serverless. It does data versioning and diffs. It's storage agnostic. You can use local storage. You can use S3. Anything you have SSH or SFTP access with like SSH keys, you can use. And it ensures that versions are captured for data code in the model. It works in parallel with Git by leveraging gitignore. The syntax for DVC is exactly the same as Git. So git add python.py, right? I'm version controlling my script. I drop an HDF5 file in there. Git now sees it, but it's not tracking it. If I do DVC add file.hdf5, it's now being tracked by DVC and added to gitignore. Then DVC gives me the same command line tools to branch, fork, merge data sets and machine learning model results. It turns into a machine learning model registry. So I have this current pipeline I'm working on with my current set of data and my current bits I've twiddled, right, for my results of my model. I then branch that, and I can change some of the data in that view and update my model and see how it improves without touching the main branch and the main data and the main machine learning model. And then if that works, I can merge it back in. If it doesn't work, I can destroy it and try again. It allows you to experiment and play with data and model results in the same way we play with software. Very cool with very modest changes. And this to me is sort of my Goldilocks solution. I very rarely go to GitLFS. I'm not going to pay for commercial storage. I don't want to spin up an NPM proxy wherever I am. I don't like Node. I don't like JavaScript. It's just a personal objection I have. And so I go straight to DVC for almost all my projects. LakeFS is an open source data version control and management system that brings versioning and Git-like capabilities to data lakes. It allows users to manage, track, and collaborate on large data sets through application integrations. So DVC ran outside of your software and worked like Git, right? I pull it down, I push it out, and then I do things here locally. LakeFS, you update your software to programmatically interface with your data. So instead of using DVC to pull down my data set and then run my Python with my data locally, I would update my Python with LakeFS commands that would read from the remote storage directly into memory and bypass the local storage system. And then when I write out the results, it writes directly to the LakeFS data lake as opposed to writing to local storage. LakeFS directly actions on subset of the data remotely, and it allows you to branch, merge, fork, share, collaborate, but with code, software, within your pipelines. It has support for Python and R and AWS CLI if you use Athena or SageMaker. SageMaker is like Jupyter Notebooks at AWS. It has great integration into the Apache ecosystem. So Apache Airflow is a workflow tool. Iceberg, Iceberg's a storage platform. Spark is a data tool. Kafka is a messaging platform for like sending asynchronous signals from like IoT devices. So I can have a sensor on the field and it can collect something, and then through a Kafka command can send something to a LakeFS server and do ELT or ETL workflows. It's really freaking cool, but it's hard to use. And it requires a server. So you need some IT, you need to set it up, but then you can programmatically interact with all your data. So I just said most of this. We've got the data versioning, we got the data lineage. Oh, snapshots and rollbacks. That's a nice capability where you can have a live data set and you can take a snapshot of it, and then you can start playing with it and update pipelines in real time. And then if it breaks, you can roll it back. So you can deploy 2 LakeFS servers and do like A/B testing, right? And do sort of, production workflows. Most workloads that you guys are running will not get to this point. But if you're working on like IoT devices or sensors in the field, or you're a clinician who does clinical work at a hospital, these type of things are really powerful. The amount of data we're generating, especially in the healthcare space, is just overwhelming. Our wearable devices like our Oura rings, or any spy devices that are listening to you, they can generate up to 5 gigabytes per person day, right? ICUs generate over 2,000 data points per second per patient, right? And you need somewhere to store this. And so the paradigm here is the realization of what Sun Microsystems said 20 some odd years ago, is that the network is the computer, right? You're not going to write data enclaves on the edge, right? Wherever you have these wearable devices, you're not going to have some storage platform. You need ways to interact with storage remotely and programmatically. And these are the building blocks of those type of services. So bring it all together. A lot of the things we've talked about today, you can do your own with no help, right? So anything around Conda, anything around SPAC, anything around containers, you can do on laptops, desktops, HPC systems, in user space, without having a sysadmin support and do anything. A lot of the newer stuff we talked about, like Kubernetes or Binder Hub or LakeFS, those require some level of IT. However, most of the tools you need to learn to deploy these things are programmatically based. They're software development processes. And if you know how to develop software, you suddenly know how to run IT. My son graduated with a computer science degree last year from UT Dallas, and now he writes DevOps pipelines for the backend team at Fannie Mae. And that's what he does. He has a CS degree, no data science, no IT, but now he writes, programmatically interacts with AWS that manages a large part of the mortgage market. And that actually scares me. He is only 23. He's good at his job, but it's the kind of thing which, let's be honest, gives you a career path. Science is under attack, right? If you haven't noticed. And the funding of the future of science is a little uncertain, right? But anything that you can learn that's IT adjacent not only gives you more power in your day-to-day jobs, allows you to build actual services and not shadow IT, and gives you a path forward if we decide to stop funding science altogether, right? Our corporate oligarchs aren't going anywhere. AWS, GCP, Azure, OpenAI, Grok is not going anywhere. And this is the type of workforce people need. A lot of the stuff we used to do and get paid for in the software development area are now being automated with LLMs, especially at the junior dev level. But someone has to care and feed for the AIs, right? You can be like the defectors in Matrix, and you can care and feed of the robots, right? And that's a career path, unfortunately. However, if you want to get started today, go to Access CI. Graduate students, PIs, you can create projects and you can get access to small resources, but for you to play with, right? Be curious, play with these tools. What I tell all of my students is you'll never regret learning more maths, and you'll never regret learning more Unix. Math is the language by which we communicate results. And a lot of what you're doing is gatekept by your understanding of mathematics. Unix is extremely powerful to know. And I'm not just talking about memorizing commands. I'm talking about understanding the principles of the Unix operating system. Windows and Mac OS are designed by committee. And things are not consistent, and things change. The Unix standard was developed by two beautiful bearded guys at Bell Labs in the late 60s, and it has very strict design philosophies. Because I know how Unix is designed, if I want to think about how to solve a problem or how something works, and I've never interacted with it, if I think about how I would implement it using the Unix paradigm, 9 times out of 10, that's the way it works. Very cool stuff. Lastly, another reason to adopt all these tools is to use it as a way to get a foot in the door to fund other science. As scientists, very little of the world is organized around what we do, right? You know, in the 90s, there used to be these beautiful, beautiful, big, bespoke machines which were made for science. You know, Cray YMPs and these big shared machine, and Silicon Graphics, you know, came out and went out of business about 10 times, right? And they were making these bespoke machines for very small communities. And then, you know, 2010 through 2020, we realized no one really cares about science because the amount we contribute to the economy compared to, you know, just selling stuff is small. So we have to use commodity hardware. So that's why we started using gaming GPUs, right, for accelerated computing to leverage the gaming market. And then, of course, AI has now taken over the world, and that's what drives economics, right? An A100 GPU, when it came to the market, was around $10,000. The next generation, the H100, was $30,000 for a single GPU. And that's because it's being used for AI. So how can you use AI and this sort of concepts to your advantage? Well, the National Science Foundation and other government organizations historically has funded workforce development, right? And a lot of what I did when I did this cloud native paradigms is I wrote my proposals that said, not only are we doing this cool science, but I'm teaching my students and my postdocs the tools of e-commerce, right? Of reproducibility, cloud native, containers, IT, DevOps. These are the tools that we need our students to graduate with. You know, something like 90% plus of CS students, when they graduate, are not ready to start their job on day one. And companies have these huge pipelines where they train them on things like AWS and DevOps before they can be useful. So how do you use this to your advantage? Well, hopefully at some point, National Science Foundation will open back up, and there will be workforce development efforts that are not labeled as DEI, and that we can actually get money to do this. So frame your science, your proposals, in terms of these concepts. Moreover, a lot of what I'm doing these days is I'm trying to talk to these big companies and have a come to Jesus talk with them and say, hey, historically, the National Science Foundation and the NIH, they have funded the development of your workforce. If they're no longer doing and funding your development of your workforce, who's going to train them? And so I'm trying to get big companies to invest in academic research under the guise of workforce development. So use current trends to your advantage. You have to game the proposal market, right? NSF average acceptance rate is between 5 and 10%, right, in terms of proposal acceptance rates. But if you do this kind of stuff and you tie in workforce development and broader impact, right, and outreach around teaching the tools that drive the modern AI revolution, you increase your chance of getting funding. So with that, I finished a little bit early, so we have tons of times for questions. So thank you very much for your time and attention. And what questions do you guys have? Yes.
Would DBC be used for binary files?
Yeah, the question is, can DBC be used for binary files? Yes, it does binary diffs. Yeah, no problems. Yeah.
All of this, when you have a group which has multiple graduate students who are all working on their own experiments based on some central Git repo that they've all forked off of, and they're all trying to manage their own experiments, how do you organize all of it?
Yeah, so the question is, in a research group, you have multiple students working on multiple projects. How do you manage all the interactions of it? So, it's kind of case-by-case basis. Some research groups have each graduate student working on a project, right? So there it's pretty simple, right? Some groups have one monolithic project that everyone works on. So there, you need to understand if you're going to work on a branch merge model on a single repo, or if you're going to work on a fork branch merge PR model. The former is where you start. The latter is when your group gets to a certain critical mass where it becomes hard for one PI to understand all the changes, right? So I say, it takes a village to raise a computational scientist, right? The pedagogy for creating a computational scientist still really isn't there today. And we all do experiential learning. You learn from your PI, right? And you learn from your research group. And when I started computational science or computational chemistry, my PI was the person who wrote the software. And so he knew a lot. But he would only take 2 graduate students at a time because it required a lot of people time of his time to help us understand the 1.5 lines of Fortran 77, right? So you couldn't scale very big there. These days, every research is doing computation. Every single problem has computation involved. I say there's 2 types of scientists. There's those who have a computational problem and those who don't realize they have a computational problem. Spreadsheets are computation. Don't do science in spreadsheets. Spreadsheets by definition are not reproducible. You have no idea who twiddled that bit or changed that field or what happened there. Spreadsheets are not science. I'm going to get upset. Spreadsheets are not science. Start using the tools of data science if you're doing spreadsheets. Alternatively, there are some really cool no-code tools that put a spreadsheet interface on top of an SQL database. And so you as a user sees an Excel or Google Sheets interface, and you twiddle a bit, that turns into a back-end SQL. And so and SQL by definition is declarative history, auditability, et cetera. So you have all the metadata about those operations. Better yet, learn pandas, learn data frames, learn how to programmatically interact with your data, learn NumPy, learn SciPy, learn scikit-learn on your local laptops. Then, when you go to the HPC system, you use NVIDIA Rapids. NVIDIA Rapids is a collection of open source tools that allow you to just change the package that's loaded and get GPU accelerated pandas, GPU accelerated scikit-learn, GPU accelerated NumPy, et cetera. I'm not sure how I got there from your question, but let's go back to that. So we've got it was raising a village. Yeah, it takes a village to raise a computational scientist. These days, every group has a computational problem, and the PIs usually know less than some of the graduate students in the more applied fields, your psychology, your business, et cetera. A lot of times, the graduate students or the postdocs know more. So when you get to that point, then you really need to get to the concept of code review. So code review is when you have a PR, or pull request. So your workload has gotten over a critical mass. You have multiple students working on a project. There's not one overarching person who understands how everything works and can understand when something breaks and when it doesn't. So you need to control the project by committee. So you have a monolithic repository that's your production repository. Everyone forks off that repo to their personal GitHub. They branch, they play, they merge, they test. When they're ready to bring it back here, they do a pull request that creates a ticket in GitHub. And then you have a code review process where you have ideally at least 2 people look at every PR and sign off on it before it's merged. But does that answer your question? answers about 20 different questions. Of course.
Graduate students working on different experiments.
Mhm.
Do they merge all into this main repo, or do they stay living on the individual forks, or do they all?
So I would have a main project and then maybe multiple repos under that project. And everyone who's doing it forks and work from there. Then, if you start getting into these really curated data sets where you need to share or exchange with the community, then you get into the concept of research data management tools. And those are things like old school tools like Dataverse, new school tools like Invenio RDM. Invenio RDM is the open source project behind Zenodo, which is CERN's research data management. And so I'm only scratching the surface here of how I actually do things. What I actually do is when I showed you that Git tag where I was publishing my results, I actually have an API call to Invenio RDM server, which generates me a DOI. And that DOI is now that number. And I can plug that number into any browser, and I have everything I need to recreate any science I've ever done. Right? That's when you really start getting the power of convergence of scales, when you take the philosophy and adopt it for everything. So the goal of this lecture was to introduce you more to the philosophy and give you a couple of examples you can start playing with. But this is 101, right? And we can go all the way to a graduate level class and do this kind of stuff. But it's really cool. It's really fun stuff. However, you have to be very careful because you still have to do some science, right? You can spend all day twiddling and making things pretty. So it's tough to find that happy medium. That's something I always had trouble with. I tend to geek out and do the most amazing job at the smallest, most inconsequential thing, because the hard problem I really don't want to do, right? However, these type of activities are good for doing in the afternoon or really early in the morning before you get to the majority of your workday. I treat it more like chores, like housework. And I do a little bit every day and clean things up. And then in your GitHub project, you create a list of issues for things you want to add, right? And you keep a list, and every so often you want to go bang things out. Science and training a computational science is all about doing a real project and banging your head into a wall until you tunnel through. And that is endlessly frustrating, and you have no idea a priori how long it's going to take to solve a problem. So I tell my students and people I work with, always think about the big problem, but always have a list of tasks that you know if you dedicate an hour to it, you'll make progress. The one thing that made my PhD really hard was that every day I went to bed knowing I made no progress. I have to try something else. And we're told a null result is still a result, but it doesn't make me feel better. So it's nice to have these small little maintenance tasks that you can do either in the morning to say, oh, cool, I got stuff done, let's try something hard. Or 2, 3 o'clock, you've maybe had your afternoon coffee, you're still a little tired from lunch, and you say, let me check off a few of these house cleaning activities, right? And it makes you sleep better, and it makes you feel like you get progress. And research is a lot about psychology and momentum, and I find it really helps. Other questions or comments? Yes, what do we got from online?
My data science pipelines always include milestone data drops and restart and abort the pipeline midway through rather than starting. But that takes up space and time. What's an efficient compression step for creating data drops?
Depends upon your data, right? I mean, some data is compressible, some data is not. Some data prefers different compression routines. You know, that's kind of really hard to say. However, I don't keep most of my data on my local systems. I keep them mostly in the cloud, and I only pull down the subsets of data you work on. But it sounds like you have a problem where your project's a little bit bigger than the resources you have available. So I would encourage you to look into some of these resources, like Open Storage Network, Access, NRP, to see if you can get some community storage for your science project. Because there are a lot of resources out there to help you. Yes? Data Lab? I am not familiar with that. Is it open source, commercial? Okay. Nice. Is it like a GUI or command line? Okay. So it's a tool, if I had to guess, it's a tool that uses a lot of this philosophy that's an opinionated deployment, right? So that brings up a good point. So I'm going to tell you guys the same thing I tell my kids. You're not beautiful, unique flowers. Every problem you have, there's at least 100 people who've had that problem as well. And at least 10 of them have tried to scratch their own itch. And at least 1 or 2 of them have probably done a good job. So anytime you sit down thinking, I need to create a new tool, as someone who now maintains about a dozen tools for the community, when I thought I had a bright idea to create a new tool, consider that choice very carefully. Because creating your own tool increases your maintenance burden, especially if it becomes pivotal to your infrastructure, or it becomes pivotal to your research group. So in this case, instead of creating a bespoke pipeline for your architecture using my building blocks, there's probably a good solution out there which does similar things. So if you take nothing away from this talk other than the philosophy and terms to Google to find people who've tried to scratch your itch, that doesn't sound very good, then maybe you'll save yourself some work. But science is really a balancing act between writing software, doing research, and using other people's software where you don't have to do it, right? It's tough, and it's a very complicated multidimensional problem, and every project within every discipline probably has an optimal solution, right? And so that's why I focus more on the philosophy and options as opposed to giving you an opinionated approach. Yes?
What's the homeland fragment the tools here so that you can gain experience using and learning without some proposal to get access?
Yeah, so the question is, yeah, a home lab is a IT infrastructure you run at your house in order for you to play stuff, right? Play with stuff. And, I have a huge home lab. And so home lab tools you can play with is the easiest thing to start with is some form of virtualization. So you can spin up virtual machines. If you're on Windows, of course, there's Windows Subsystem for Linux too, where you can spin up, Ubuntu and Rocky virtual machines on Windows. There's things like VirtualBox, which are free. And you start there. Then you move to a tool like Vagrant. Vagrant is a virtual machine as code tool. So you write declarative Vagrant, and then at runtime, it'll spin up VirtualBox or VMware or whatever virtualization you're using. Install Docker Desktop and start playing with Docker containers. And if you can convince someone who has money, have them buy you an NVIDIA Spark DGX, NVIDIA DGX Spark. These are these new little $4,000 NVIDIA workstations. And they come with the full DGX OS stack, the full NVIDIA AI Enterprise stack. This little box is a 20-core ARM processor with 128 gigabytes of unified GPU CPU memory. So you can do 128 gigabyte AI workloads. And it comes with the full NVIDIA AI Enterprise software stack. And that software stack is a couple of $1,000s per GPU per year. Now, this little $4,000 box is not hugely performant. Your gaming desktop with a 5080 or 5090 will beat it. But the ecosystem and the tooling is what you need. Ultimately, what we're going to see are these DevOps playbooks that take you from a DGX Spark to an HPC system to the cloud using the same tooling in these DevOps frameworks. What other home lab tools are great? I run the OpenHPC project, and we have ARM support. So I run OpenHPC clusters on Raspberry Pis that I do test dev on, and that's you can build a really cheap, 4, 5, 6 node Raspberry Pi. Interconnect them with 2.5 or 5, 10 gigabit networking, but 2.5 is fine. And then you have a nice little environment for playing around with. Eventually, you'll want to upgrade to Kubernetes. You can start with something like, micro K8s or K3s that can run on a single node, and you can play with a Kubernetes or a K8s API endpoint locally, and then eventually go out to a distributed system. But Home Lab YouTube is great. So I recommend just searching around and looking for like level 1 tech is a good one. What are some other good Home Lab ones? Was it Network Chuck or something like that? They have really cheesy names. I kind of don't want to say them all. But look up Home Lab YouTube. There's some really great resources for playing. Yes?
Excel so that my BI can evaluate data, interact with it as I see that. What are good tools or export to Excel?
Whiskey, bourbon, scotch. So it happens, right? Sometimes you're gated in what you can do by your PI. What I will say is there's some very nice tools that you can use with Google Sheets to create them programmatically. And then you can look at versioning to watch what they do and then manually update your stack. One, you can install a keylogger on their system and see what they do. But capturing metadata when interacting with a spreadsheet is almost impossible unless you treat it like chess and you write down updated number in cell C6, right? It's just spreadsheets are not made for that. And that's why I really encourage people not to use spreadsheets. Any other? I think that's 12:30. I think it's time for lunch. So great morning session. 2 hours down, 2 hours more of listening to me, and we'll start in an hour. Thank you very much. So we spent the morning talking about reproducibility. So now let's talk about things that are inherently not reproducible. Let's talk about large language models. It's not entirely true, but we'll talk about that in a little bit. But before we get started, I want to talk a little bit about Cambridge Computer and how you can engage us. So as I said, I'm a scientist in residence at Cambridge Computer. Cambridge Computer, we're called a VAR, a value-added reseller, which is a fancy way of saying we're a glorified parts catalog, right? And our business model is around research computing, and we have experts like me on staff consulting, and I'm 100% flat compensation. I have no sales incentives. And so one of the services we offer, if there's any PIs in here who are writing proposals, we can help pull together hardware bills and give you quotes for that. But in exchange for working with us, you get my time. So I often help breadboard out proposals. I help review and help you name them for the NSF program reviewers. And I was an NSF reviewer for 20 plus years, and I've had over 100 funded projects. And so that's one thing we do in Cambridge Computer. We have experts at the intersection of AI, IT, data, and science. And if you're a student and you're a graduate and you're interested in coming to do some of the things like I do, feel free to send me a resume. We are always recruiting, and I'm building sort of a stable of scientists that are in this space who kind of do what I do, and I'm trying to train and do workforce development in the commercial space. You have my contact information. We also have, is James around? No, James isn't around. Never mind. So, there's James. James is the relationship manager for Cambridge Computer from Minnesota. You can reach out to us, and we're here to help. If there's anything we can do to help you out with your proposal or any hardware you're buying, just let us know. We are an NVIDIA 5-time Partner of the Year. We're the only multi-time Partner of the Year. We're one of 8 SuperPod certified vendors in the world. We deploy and all these big new AI systems. So yeah, reach out and let us know what we can do to help. So let's talk about open source LLMs and how we can run them and start playing with them on the resources we have. So one of the comments I made on my first slides, and one Graham pulled me aside to talk about, was I said, in the AI workspace, we probably need more tools than just batch HPC. Now, right now, most LLM and AI workflows are still at that prototype experiential stage, and the resources you have where there's a bunch of GPUs are Slurm systems for the most part. So we're going to talk about prototyping and experimenting with these, but longer term, know if you want to spin up an inferencing endpoint and actually run something in production, you probably don't want to do it on your Slurm system, right? You don't want to wait in the queue while your inference job spins up while your autonomous vehicle is waiting for instructions, right? And that's why we have things like Kubernetes and cloud native actual resources to run on. So today what I want to do is introduce LLMs and talk about the justification for local deployment. And again, if you're writing proposals around these things, take these nuggets, right, that I put in here and use them in your proposal. We're going to talk about the open source model landscape and compare models together. And we're also going to talk about open source frameworks. Frameworks run models, and multiple models can run on the same framework. And we'll kind of look at that space. Then we'll talk about how to integrate them with traditional research computing, batch HPC, and open on demand, right? You have on demand, the web portal. We'll talk about how to leverage that for AI workloads, especially around spinning up like coding environments and code completion using open source tools. Then we'll talk a little bit about RAG pipelines. Does anyone know what RAG is? Resource augmented generation? Yeah, whenever you drag and drop a file to give it context, that's RAG. And we'll talk about that, and we'll talk about how to spin up RAG pipelines on your HPC system. So the goal of this is to understand LLM deployment trade-offs when you do open source, when you do closed source, how to select appropriate models for your application and infrastructure, or if you're writing a proposal, select infrastructure to go with the models you want to run, because you'll see very quickly it's pretty impressive how much resources these LLMs need to run. And lastly, I want you to understand how LLM workflows can be run on Slurm and open on demand to start prototyping and start playing with these resources without giving your data to Elon Musk, right? All right, so what are LLMs? I mean, LLMs everyone knows in terms of the chatbots, right? And LLMs really started taking off when the transformer architecture was first released. There's a canonical paper, 2018, 2017, something like that. It's called Attention is All You Need. It talks about the concept of the attention cache and how that's able to give context for a model to make it smarter. Transformers are not magic. They're not answering your question. They're word calculators. That's all they are. Given the current word and the context, what's the most probable next word, right? That's what it does. They are statistical generators that every time you run it, unless you twiddle a couple of bits, you'll get slightly different answers, and sometimes you'll get dramatically different answers, right? We're going to talk about foundation models and how they're trained, how big they are, and how they're broadly applicable, and then they can be fine-tuned to specific tasks. We're going to talk about reasoning models and how they're foundation models that are equipped with not really problem solving. They're more, they're more have sort of a decision tree where based on your context, they can do different iterations to help solve your problem more precisely, but they require more resources, more GPU time than your typical foundation models. And we're going to look at key capabilities for research computing like code generation and debugging, scientific writing assistant, data analysis, literature review and summarization. This is what I use LLMs for almost exclusively. I love it being my graduate student. When I was a faculty, so I'm a quantum chemist by training, so everything talks about operators. And so we always had a joke. I don't say it's funny, we were chemists, but we always had something called the grad student operator. Was when we wanted something done, they would just go turn the crank until it was done. And the main reason I use grad student operators were for doing literature reviews and research. LLMs are really good at that. And domain-specific knowledge extraction on how to extract data from images, from papers that are context and scientific domain specific. So why local deployment matters? First, data privacy. Your data is being used to make a ton of money, right? Most of the money is being made by NVIDIA. Most of the companies aren't making a ton of money right now. In fact, they're operating at a loss. But they're trying to profit off your data. And if you look at these EULAs and read them when you start using OpenAI or Claude or Grok, they're pretty egregious. Also, if you're running on-prem, you have a reduced latency for interactive workflows. It makes a pretty big difference, especially with like IoT devices. These days, there's no longer really unlimited tiers in a lot of the big closed source models. And it's not that hard to generate a query. All of a sudden, you're spending several $1,000s just for a single result, right? There's something very interesting here. You've probably heard the concept of agentic workflows. We're not really going to talk about those today, but agentic workflows is where you start strapping multiple of these domain-specific models together for specific tasks, and you chain them together. And we're going to talk about something as the attention cache, as well as the context window. And for almost every LLM architecture, memory usage just scales quadratically as the size of the context window. So if you double the size of the context window, it's now using 4 times more GPU memory. And now when you're chaining 10 of these together, you get these really big million-plus token context windows, which translates to a lot of money. We're going to talk about what models have been customized for domain-specific needs and what models you can maybe bring your own data inside of and not just use RAG. You can actually incorporate the corpus of your data into the model weights. These last two sort of align with what I was talking about at the end of the last talk with, again, you use these concepts to justify workforce development, to give your students and staff experiential learning, so they'll give you money to do the science you really want to do. And lastly, we need a ton of GPUs for things like protein folding and molecular dynamics, and you can use this as a justification to get more GPU resources, right? Talk to campus leadership. They understand ChatGPT needs GPUs. They don't understand necessarily that protein folding does, right, or your CFD does. So you can use this politically to get more money to do science. So commercial solutions, there's a lot of them out there. The big ones I'm going to, are OpenAI, Claude, and Perplexity is what I think the big ones are. I do not include Grok on any of my analysis or any of my benchmarks. I don't believe anything that comes out of Grok and XAI. And ever since Grok referred to itself as Mecha Hitler, decided not to play with those tools, right? I don't know if you're following, don't want to get into politics, but Elon plays with the prompts of Grok to make it edgy, right? And that's not what I want to do my science with. I also, when I'm going to look at the benchmark results, I'm only going to include OpenAI up to V4. I'm not going to include V5. So I have some colleagues at OpenAI, and I've had access to V5 for a while. And when V5 was a private beta, it performed very well. And now that it's in production, performance has degraded. There's a couple of reasons for that. But more importantly, these commercial models are no longer single models. They're a group of models. And when you hit the API endpoint, based on your query, it routes it to different models. And that makes benchmarking almost impossible. Claude is really good at coding, has great command line tools, but Claude does this dynamic routing, but they do it for a different reason. Anthropic does not have the money that the big boys have. And so they're constantly taking GPUs out of their inference pool and putting it into their training pool, so the quality of the models go down. So it's really hard to compare. Perplexity also does dynamic model routing, so I'm not going to compare any performance results to Perplexity. However, Perplexity is the only commercial service I pay for. I pay the $20 a month Perplexity membership, and I think Perplexity is the best research tool. It has really good access to scientific journals, and that's what I do most of my research with. Everything else I do on-prem in my home lab with open source Libre gratis models. The cons of commercial solution, of course, are the recurring cost, data privacy concerns, rate limits, and dependencies on external services. You might have noticed last week the entire world went down when AWS US East 1 went down, right? US East 1 is the most critical zone for AWS service, and tons of things went down. And if I'm doing something mission critical, I don't want to rely necessarily on that. Open source on-prem solutions, full control, no recurring costs other than power and cooling, which is actually quite a bit of money these days. The data remains local, they're customizable, but you have to manage your own infrastructure, and there are performance gaps. The open source market is behind, but it's catching up mostly thanks to China and the work they're doing there around open models. So when you're thinking about working with LLMs and research computing, you have to worry about sensitive data. That could be data with a classification. It could be data you're not ready to publish yet. It could be PII information with credit card information or stuff like that. You want something that has batch processing capabilities because we're going to do these on HPC systems. And a lot of times we want to do multiple prompts at the same time as opposed to interactively. And we want tools that integrate easily with the command line and Slurm. So the models we're going to review today are DeepSeek and Llama, and we're going to review those in great detail. I'm going to start by talking about the DeepSeek family, because that was the first open source model that was really disruptive. And it actually impacted NVIDIA stock for a bit, right? And there's a lot of privacy concerns about it. Now, when I say running DeepSeek, I don't mean using their API endpoint on their servers, right? I'm talking about running it on my own hardware. I would not use DeepSeek's commercial service. Llama really started the open source trend, and it's Meta, surprisingly, released the first of it. But we're going to kind of compare DeepSeek and Llama. And Llama is a really nice illustration of how benchmarks can be gained and look better than the model actually performs. And there's a reason why Meta's closed sourcing its models. They're behind, way behind. And they're hiring individual people with salaries of $1 billion each, right? And what that tells you is that a lot of this is not science. A lot of creating an LLM is art and gut feeling, right? And so it's not well established. Then we're going to talk about some specific models. Gemma is the open source version of Google's Gemini. We're going to talk about Mistral, which is a really single node optimized code powerhouse. We're going to talk about Quinn, which are really efficient, small, elegant models. And then we're going to talk about Bloom, which is the most open model in the world. So when we talk about an open model, there's a couple of different ways it can be open. One is open weight. And that is you can just download the parameter values and run it locally, but you have no idea how it was trained, right? And then you have open source models in which they have a repository where the code is that maybe the model was developed with. And then there's Bloom, which is 1,000+ people working worldwide that published papers of every step of the way how they developed and trained the model. Bloom performs the worst by far in terms of hardware utilization and efficiency. But it's a very open model and has some novel use cases, especially around equitable access in foreign languages and non-Western scientific traditions. When we're going through these models, we're going to look at the accuracy and the benchmark performance on specific domain-specific tasks. We're going to look at the tokens per second throughput, the inference speed. We're going to look at memory efficiency and VRAM requirements. And we're going to talk about quantization. Quantization is the floating point precision you run the model on, which influences how accurate it is versus how fast it is versus how much memory it uses. And lastly, we're going to look at some domain-specific applications from like edge to medical, and look at where we can have these specific models that have been optimized for particular use cases. Any questions so far? We're good? All right. DeepSeek. DeepSeek model family has two distinct branches. There's the R versions, the reasoning versions, and the foundation models, which are the V versions. The reasoning models are designed for step-by-step logical inference and breaks a problem apart and searches them one by one and iteratively solves the problem. Foundation models are optimized for more general purpose language and understanding. They're trained to be communicative first, and then you optimize them for particular tasks. Foundation models can be single shot or multi-shot in terms of how it runs and how it works with the data, and that kind of depends upon the architecture of the model, and we'll talk a little bit about that as we go through these model families. DeepSeek is the most performant open weight and open source model. The code repository are MIT licensed, so you can just pull through those. And if you're really interested in CUDA and architecture and accelerated computing, reviewing this source code is the most educational exercise I've ever done. So I'm going to do an aside because I think this is really cool. So, the United States put restrictions on what GPUs can be exported to China, right? And the restrictions are around the hardware on the chips that do nickel, NCCL. Nickel is the NVIDIA Communications and Collectives Library, and it's like MPI for GPUs. It gathers all the data and sums them up and handles the parallelization. Well, it's this nickel which allows you to scale horizontally and use GPUs across multiple nodes with a manageable programming interface. And so the US government said you can't sell GPUs with this hardware accelerated collectives on it. So they removed those transistors from the chip. They put extra compute cores on it in its place. And then instead of $30,000, they sold them to China for about $12,000. Okay, so the CUDA stack. CUDA goes CUDA X at the highest level, which you as a user tend to write the APIs against. Below that is CUDA. And CUDA is the API, what you write your C languages in. It's how you actually prototype it. Below that is Nickel, which is the Communication and Collectives Library. Below that is PTX, Parallel Thread Execution. And PTX is kind of like the assembly of NVIDIA GPUs. And the DeepSeek team rewrote the entire collective stack in native PTX. Performs better than Nickel. And they have more hardware to do more compute on fewer, with cheaper GPUs. So the tariffs and the export restrictions actually advance the state of the art. So I think that's kind of cool. And if you want to learn a lot about PTX and kind of assembly and how you actually programmatically access these GPUs, just reading this source code was actually very entertaining to me. Learned a lot. And if you ever get bored one night and can't sleep, go to their GitHub and poke around. It's actually really well done. And then for using the model weights, they have a custom DeepSeek license that dictates its usage. So you can use it for commercial use, but there's limitations. For research, we can do anything we want with it. All right. So the R1 model started with the release of the R model started with the release of R1 in January of this year, and then R1 0528, right, on 5/28. And we're working towards R2. R2 is not available yet to the public. So the model philosophy for DeepSeek is it's a reasoning-first approach and has a very visible thought process. So you can actually see the steps it's going through. And it's really interesting and educational just from a pedagogy standpoint to understand how these LLMs function, how they work, and how prompt engineering and system engineering works. They're very good at mathematical and scientific problem solving. And they use an MOE architecture with dynamic routing. MOE is a mixture of experts. So the first original architecture for transformers were a dense transformer architecture, and that is the number of active parameters during an inference is equal to the total parameters in the system. If it's a 7 billion parameter model, 7 billion parameters are active. MOE starts with a routing model that looks at the context and figures out which of the experts it should use. And the experts light up subsets of the parameters. And some of the experts overlap in the parameters, some of them use different parameters, and they have different use cases. And that means it doesn't change the memory requirements, because you still have to load the full parameters into VRAM, but it does change the computational runtime, makes it much faster, right? It also makes it better and reduces hallucinations. It's kind of a cool architecture. This was created, again, around Chinese research, very mathematical and scientific focused, code generation, and really good at research paper analysis and synthesis. R1 0528 improved the model. So we're going to start looking at number of parameters. This model has 685 billion parameters. It's a 14 billion increase over R1. Not a huge increase. 37 billion parameters are active per token. Do we know what a token is? So a token is a mathematical mapping from characters to numbers, right, in some distance metric. And on average, a token is 4 characters for the English language. And that includes spaces, commas, punctuation, etc. So a token's about 4 characters. Context window is 64,000 tokens. And that's the output and input space that the model can keep in working memory, right? Larger context windows can do more complicated stuff, but your memory uses scale quadratically as the size of the context window, so choose carefully. Mostly what's different between R1 and 0528 is enhanced training or enhanced optimization during post-training. So training is when you teach the bot to speak, right? You give it birth, right? And then you teach it specific activities. That's post-training, right? All right, and here's some performance improvements. AIME is a math benchmark. This is a general purpose reasoning benchmark, and here's some coding benchmarks. And all we've done is done some post-training, and we've changed a little bit about our system level prompt, and we see significant improvements in our model performance. Most of the benchmarks I'm going to show today, I've run personally, or I've had a colleague run who I trust. I'm not very happy with the way the LLM benchmark space is working. Most of them are simply Twitter accounts where they aggregate results, and I don't use Twitter or X or whatever you want to call it. I just refuse to. So I'm mostly pulling these from what I consider to be trusted sources. So reasoning capabilities improved over R1. As I said, the reasoning depth has increased. The reasoning depth is the context window for the reasoning steps. So that's increased, almost doubled in size. And that right there reduced hallucinations by 50%. That gives it more context for while it's thinking. It also has function calling support, which allows integration with external tools and are sort of the building blocks for you to be able to build programmatic pipelines for interfacing with LLMs and are the stepping stool to agentic workflows. I would like to point out this really cool distilled variance, and this is what I think is really interesting and where in EDU we should really do some cool things. It's really expensive to run the big foundation and reasoning models, but a distilled model is one in which the parameters are trained on the outputs of the reasoning step of the foundational or reasoning model. And so you use one model to train another model, and you make them very application and domain specific. And it's this type of approach that really saved DeepSeek. So it's almost impossible right now to start up a new closed source LLM company. OpenAI was first. And when OpenAI started, they were able to pull down the entire internet. Twitter had no API limiters. Reddit had no API limiters. Facebook, I hope they didn't use, but it didn't have any API limiters either. And of course they used it. And so the companies that started first were able to aggregate huge, obnoxious corpus of data that today, if DeepSeek wanted to pay the API costs to generate the data that OpenAI has, it's estimated to be about a $50 billion charge of API costs. So what did DeepSeek do? Well, DeepSeek paid for commercial licenses of ChatGPT and used ChatGPT to generate its own copy of the internet. It regenerated Reddit. It regenerated Stack Overflow. It regenerated Twitter from the model weights in the corpus that's in OpenAI. And then they fixed things. They fixed common programming errors. They fixed misspellings. They probably got rid of some propaganda. But it improved model performance significantly. And this is another reason why I don't use Grok. Because Elon is on record saying his goal with Grok is to use it to rewrite the internet to get rid of liberal talking points or DNC talking points or political things and create his own Elon internet, which he then used to train Grok. And if you've ever seen some of the conversations people have with Grok on Twitter, that's kind of concerning. So this was a really cool advancement, but it's very powerful, and it's probably going to be in the wrong hands. And so you, as scientists, you need to really understand how these work and be on the lookout, right? You can't trust search results anymore, and you can't trust LLMs, right? You know, we say things like trust but verify. Don't trust, and verify many times before you use any output from an LLM. LLMs will not give you an answer that you can use directly. For me, LLMs are a preconditioner or a starting point. It's easier to edit than create, right? But you have to check everything. All right. Other cool things is they have a structured output with JSON output. So if you want to programmatically parse outputs through conversation of batch LLMs, you can do that. Again, it added the tool use capabilities, and it has multiple frameworks that it's now supported with. R2 is what they're working on now. They were supposed to release it this summer, but they've kicked the can down the road to do some additional optimization. My colleagues who work on these projects say that the results are very interesting. So I've got a bunch of colleagues I work with in China, and we sort of share developments together. And so I'm going to give you some preliminary results on what we expect it to do, but don't take this to the bank. 1.2 trillion parameters are going to be in R2, and 78 billion activated in a hybrid MOE model. It has an improved neural architecture, improved training methodology, which I can't discuss yet, and multimodal capabilities, which means it can process more than just text. It can process vision, images, audio, things of that nature. Early testing shows it's a 40% faster than R1, even using about twice as many parameters, and that's because of these novel architectural improvements, which have not been published yet. Accuracy shows about a 35% improvement in complex multi-step tasks, while having reduced computational requirements. Because the DeepSeek guys have had to write PTX and not nickel, CUDA, and CUDA-X, they're able to route around bottlenecks that the CUDA architecture implemented early on that they can't necessarily rewrite because of backwards compatibility. So they're kind of got the advantages of the GPU ecosystem without being locked in on old design decisions. Also has enhanced multilingual reasoning. Some of the early DeepSeek models weren't really trained on multiple languages as much as a lot of the closed source models. It's getting there. All right, so those are the reasoning models. The foundation models are more the general purpose conversational bots. And then these models are then what are used for fine tuning or domain specific specialization. It's an MOE model, mixture of experts model, but it implements a yarn technique for really long sequences. So I was telling about context windows. Context windows is the static maximum amount that can go in and out of a model. Well, yarn is kind of like out of core workloads for LLMs. When I say out of core, like imagine I'm running a compute workload that requires a terabyte of RAM, but my local system only has, 512. Well, I'll write partial of the project to RAM, calculate on that, write it out to disk, read the next part, write it out to disk, and then solve those gradually by using multiple techniques. Yarn works the same way. And so you can have really long multi-million token context windows if you're willing to hit the performance penalty. But that's a cool capability. And that's why it targets more scientific literature processing. Because if you're processing the corpus of a topic in journals, it's very easy to get over several 100,000 tokens. So this allows a much larger attention cache, retention cache, and reduces hallucination significantly at the cost of computational time. V2.5 is the latest version of the 2 series. And V2 was sort of this economical training pioneer where I told you about. I told you it would cost them around $50 billion to generate, with API calls, that data. DeepSeek says they only paid $6 million in ChatGPT costs in order to regenerate the internet. I'm not sure I believe that. I expect it to be much higher, but that's what they've published. Now, when V2 was released, there were then specialized variants that did for chat, for improved communication, and Coder for their programming models. Well, V2.5 combines those by using a modified version of distilled technology and has the same number of parameters and same activated parameters. really great at instruction following, and now has fill-in-the-middle code completion. So previously, it could do some coding, but you would give it a single task, and it would do the full shot. Here, you could actually integrate it with an IDE like Claude and have it do code completion, right? That's a different type of training that you do. And again, JSON output and tool integration like R10528. V3 is available, but it's a pretty big model. It's about the same number of parameters as the R models, 37 billion per token. And look how it performs against ChatGPT 4o. General reasoning, well, Claude, I can only say competitive because Claude changes model fidelity over time. In math benchmarks, it's doing better than GPT-4. Human eval, which is a coding exercise, it's doing a little bit better. BBH is a general problem solving. It's doing really well compared to ChatGPT-4. So here is a list of the model family. And if you ever wanted to have your own version of another OpenAI model you used, here's how the OpenAI models, and Claude for V3, because it now is a man-in-the-middle, code-in-the-middle completion. Here's how you choose a DeepSeek model that's equivalent to their OpenAI or Claude peer. So here we compare the DeepSeek models against each other. Here's my very precise metric of superior being greater than outstanding, greater than excellent, greater than very good, and greater than good. And you see a couple of interesting things here. Orange is the top level, blue is really good, and black is just what it is. So for mathematical reasoning, R10528 is outstanding and is what you would use if you have the GPUs that can run this. This is a 600 plus billion parameter model. V3 is not as good, but it's a much less expensive model. Code generation, V3 is something I would use over a reasoning model for code generation. Not for code completion, but for code generation. And here we have the R2. Early results look like it's better at everything, but it's 1.2 trillion parameters. So I keep saying these parameters and these models are big, so let's learn how to calculate memory requirements of an LLM. All right, so the basic formula is the memory in gigabytes is equal to the parameters in billions times bytes per parameter, and then I add a 20% overhead, right? So a billion parameters, 10 to the 9th, gigabyte, 10 to the 9th, right? Okay, so this is where quantization comes in. Is everyone familiar with like FP64 or double precision versus FP32 and single precision? Okay, those are the number of those. That's the size of our data type, right? That's the amount of bits we have to store that number, right? That's the number of bits which are divided between the abscissa and the mantissa, or the decimal term versus the power in scientific notation, right? And so 64-bit gives us, this really big domain where the epsilon, the minimum error, is 10 to the negative 16, right? Really accurate, and we really need FP64 for numerical methods and convergence and what I did in quantum chemistry. Single precision is FP32, half the number of bits, right? Reduces the memory by 2, right? And that's used a lot in protein folding, molecular dynamics. If you've ever heard the concept of mixed precision, that's sometimes using different precision types based on the requirements for that type of calculation. Now, LLMs use, for inference, FP16 or lower. So FP16 is 16 bits. There's 8 bits in a byte, so that's 2 bytes. So if I have a 100 billion parameter model in FP16, that's 200 gigabytes of GPU memory times 20%, 240 gigs, roughly. That depends upon the context window and how much data, but that's just a ballpark. FP8 halves that to 100 gig. FP4 halves that to 50 gig. FP4 is only 4 bits per number. And if I knew that the results didn't matter, we would have all finished our PhDs a long time ago, right? But here in LLMs, It just has to be close enough, right? LLMs essentially are a form of semantic search, right? And when I have two words, dog and cat, right, and I tokenize them or actually convert it to a vector embeddings for a RAG model, that generates some number in a distance metric, right? And then if I run canine and feline through it, it generates two different metrics, and canine is closer to dog than it is to cat, and feline is closer to cat than it is to dog. And that's how semantic search works, very broadly, right? And so does it really matter if the metric is 27.00001 versus 27.00? Especially if you're just having a conversation, not so much. Now, when tuning and training, sometimes you'll use FP32, and you mostly use FP32 for the gradients, because the gradients, right, the derivative, that really influences the action of the model. So a lot of times you'll use FP32 for the gradients and FP16 for everything else. But when you're doing high-speed inference, you're really doing these at much lower precision. Now, FP16 was introduced with the Ampere model of GPUs. You might have heard like an A100. That's when FP16 was introduced. Hopper introduced FP8. You might have heard of like an H100 and an H200. And Blackwell, which is the most recent generated, introduced FP4. It's not actually FP4 due to the IEEE definition. It's actually an NVFP4, which is an NVIDIA specified FP4 designation. I'll leave the rest as an exercise for the reader. And the way they actually did their NVFP4 is there's minimal accuracy degradation over FP8. Now, here's some actual examples of a 70 billion parameter model that I ran on FP16, and I ran it many times with different frameworks and different queries and different context windows. So 70 billion, FP16, two bytes per floating point, so 140 gigs. 20% more than that, right, is 28, so 168. And then there's the KV cache, the key value cache, there's the activations cache, and there's some overhead due to CUDA kernel's workspace and the framework. And I had examples in the 168 to 187 range. Most of them were in the 168-ish, 170-ish range. So pretty good. Maybe add 25%, you know, but ballpark. So let's now look at those models we were talking about and how that maps to hardware. DeepSeek R1 is 1.6 terabytes of RAM in FP16, right? A DGX node of the Hopper variety has less than a terabyte of RAM. A Blackwell has right about the amount of RAM to run this single job. And that node commercially is $800,000 for that single compute node, right? EDUs, roughly 400K, a little bit lower, and even lower if you buy it from us. Then let's look at DeepSeek R2. We're now at 3 terabytes for a simple inference. We're talking multiple $1 million worth of nodes to do a single query. And that's why we use lower precisions, right? FP8, FP4, really big one. We're still getting down to less than a terabyte, 720 gigs, but this I can run on a single node. All right, for LLMs, if you're working on HPC systems, I recommend a minimum of an A100. Now, if you have NVIDIA, 5070, 5080, right, even a 40 series, it'll actually perform pretty well on some of these calculations. They're just limited in RAM, right? Your consumer GPU cards have anywhere from 8 to 24 gigs of RAM, which means you can do 8 to 24 billion parameters on a single GPU at FP8, right? Twice that at FP4. The node that I think that has really interesting today is these 8-way RTX Pro 6000 servers. So you might have heard of the L40S. That was last generation's sort of science per watt optimal card. And the L40S was replaced by the RTX Pro 6000 Blackwell Server Edition, because NVIDIA loves naming things in strange ways. But those GPUs are about they should be 8,000 retail per GPU. The market street price right now is about 10,000. But you can get an 8-way node for about $120,000 today, and that gives you 8 times 96 GPU gigabytes of RAM, which is 768. So you could run DeepSeek R2 on a single RTX node. That's kind of cool. Smaller models can leverage the L40S, and I still recommend the L40S. It's still the best science per watt, but there's no FP4 support. It's the Ada Lovelace architecture. Some of the new architectures that are coming out by NVIDIA is very interesting. So earlier today, I talked about the DGX Spark. So the code name of that chip is a GB10. And the precursor to that is what's called the GH200. So G stands for Grace, which is NVIDIA's ARM architecture. H stands for Hopper. 200 is the model number. And they're on a single unified chip-to-chip interconnect, and they share memory. These GH200 NVL2s you can get with 2 GPUs, 2 CPUs, all in one high-speed unified memory that communicates at 900 gigabytes per second. And it has 1.2 terabytes of unified memory, and it's about $85,000, $90,000 today. So it's really nice. And these Grace Hopper and Grace Blackwell were really built for RAG workflows. So RAG, again, we will talk about a little bit later, but that's when you read your own data into memory. And when you do that, you're limited, you're adding onto the parameters, right? You're increasing your memory space. So when you do RAG, you're not always accessing all of that data at the top speed. And it automatically moves between GPU and CPU memory based on LRU heuristics, Lisa recently used. So it'll automatically migrate. So you can create tons of RAG data, keep it in memory, and only work on a subset of that. And if you're doing a lot of RAG, it's really nice for that. All right, so now let's talk about Llama. Llama was the first open source model released, and it was released in 2023 with Llama 2. It was the first open source model, but it wasn't great. It had some updates from Llama 1 in terms of context link and multimodality, and has been focused on many applications. Llama 2, 2023, they have a 7 billion, a 13 billion, and a 70 billion parameter variety, but a 4K token context, right? Most of the context windows we've been talking about are 64, 128, and we'll see some later that are million. Community license permitted broad commercial use unless you had more than 700 million monthly active users. I don't know, that was the limit on the license. They also had fine-tuned chat and code variants that shipped at launch. Last year in April, Llama 3 was released that had dense 8 billion and 70 billion models. And when I say dense, right, that means it's a dense transformer architecture. That means all parameters are active for every query, as opposed to a mixture of experts, where a subset of those parameters are lit. Double the context window to 8K, trained on 15 trillion tokens. Llama 3.1 is actually the only good Llama model. It's a 405 billion mixture of experts model, and then had distilled and revamped 8 and 70 billion varieties. And that 70 billion benchmarking I was doing earlier was on a Llama 3.1. 128K token context, we're getting there. Multilingual, both spoken and programming, and tool use APIs for programmatically interfacing with it. And license now allows using model outputs to improve other models. Llama had a specific restriction that said you couldn't use it to create a distilled variety or distilled variant. But that's gone in 3.1, and 3.1 only. 3.2 had 4 distinct models, an 11 billion vision model and a 90 billion vision model, and then some lightweight text only for like mobile apps, edge devices, which are really just meant for communicating, like kiosk applications, things like that. Llama 4 came out in April this year. And now they have multiple named variants. There's Scout, which is 110 billion roughly, with 17 billion active parameters, and a 10 million token context. Maverick, more parameters, 400 billion, 1 million token context. And then Behemoth is said to be 2 trillion parameters with roughly 300 billion active. Behemoth has not been released. I've heard internally that Behemoth is a disaster and that they're not going to release it, and Meta's no longer going to open source anything. They're all going closed source. They're behind, as I talked about earlier. Some cool things here. As I said, closed source, native multimodality in the base model for text and image, over 200 spoken languages in it, and the use policy bars EU users from using it due to compliance review and GDPR and other things that are going on. And I'm fairly confident they're just never going to do it. So here is sort of the model family. And you'll notice on the dense transformers, right, the active parameters and the total parameters are the same because they're all active. And on the mixture of experts, they're divided up. So this gives you an idea of the capabilities. All of them have the licensing restrictions except the 3.1. 3.1 is the one I would use if I wanted to use Llama and I didn't trust a Chinese model. But for almost any application, I don't think there's a good reason to use Llama today. Here's some of the benchmarking results. There's no reason to use 2 or 3. 3.1 has some really good mathematical reasoning. 4 got worse, but its general knowledge got better. Anyone have an idea what's happening here? No, these are both MOE. It's that Llama was tuning the models for the benchmarks. They were over-tuning. They were getting dogged for their poor mathematical performance. So they're like, okay, we can fix that. And they're like, this is really good. Let's try to bring this up. So they brought this up, but crashed the performance here, right? It's an art, not a science. All right. So the next thing we're going to do is go beyond DeepSeek and Llama and talk about some sector-specific and some really interesting use cases for other models, particularly focusing on smaller models that are optimized for domain-specific tasks. And we're going to look at models that have much better performance per token. So that's the second half of the talk. We got about 10 minutes before the break. So now I'll take questions if there's any in person or online. If not, we can take a break early and resume early. No questions online? Yeah.
I know this isn't like the focus of your talk here, but I'm just kind of curious as to like what goes into like this benchmarking process when you're comparing model versus other.
Mm-hmm.
Like, is there like a set of like standardized questions?
Yeah. So the question is, what goes into benchmarking a model? So you download the model weights, you instantiate them in a framework which runs the model, and then you download the benchmarking scripts. And they're just a set of prompts and answers. And there's a tool that validates the answers. All the different benchmarkings have a little bit different way to run them, but that's the general principle, is that they're just a set of scripts that drives the model for you in a pre-programmed way with known answers and then a scoring metric. Does that answer your question? Cool. Yes?
From one LLM model, let's say the newer version of how do they train the model? Do they add additional parameters to the previous version of the model, or do they completely retrain it for the completely different architecture?
Yes. It depends. So on the closed source models, they don't tell us. This is the secret sauce, right? Some of it is model continuation. Some of it is model re-architecting. In some instances where they're just augmenting the parameter space or changing the mixture of experts, then they can resume. If they're redoing the architecture of the neural nets, then they have to start over from scratch, right?
DeepSeek from its R10528, they had used 128,000.
128K context window. Yeah, and so they reduced it to 64K in which one? R2. Is it 64K? Let's look at it. Yeah, so the question was with R1, it's a 64K. Oh, R1 was 128. R10528 was 64K. Why they reduced the context window? It's because the slightly more parameters increased the VRAM. That means they needed a lot more training resources. And they have a hard time sourcing GPUs in general, right? Especially with politics going on today. So they reduced the context window to fit into their training infrastructure. R2, the public doesn't know what that context window is. Any other questions?
Very simply, how do you train these models? So I understand like provide a bunch of
Mhm.
input,
Mhm.
but
Yeah, so the question is, how do you train these models? And when he trains things in AI, you usually know the answer you're looking for. So again, this goes back to me saying it's more of an art than a science. If you want to learn how models are trained philosophically, the Bloom papers are a good place to start. If you want to learn frameworks to do it from scratch in the open source ecosystem, what you're looking for is NVIDIA NeMo, N-E-M-O. And NeMo has a couple of packages called NeMo Curator, which curates and prepares your data for an LLM. And if you're familiar with traditional supervised versus unsupervised, a lot of that is labeling. A lot of that is using older LLMs to label new data to incorporate into your model. There's a lot of tricks that are played. And there's also something called NeMo guardrails, which are like bumper bowls for your LLM, right? It's how you say don't go off the, don't call yourself Mecha Hitler, right? A lot of things they put in these LLMs around prompt engineering is really interesting stuff. Every LLM in production today has to be told that Trump is the president, explicitly. Because based on when they trained the model, they had 4 years of Reddit and Twitter where Biden was president, and they had 3 months or 2 months where Trump was president when they started training their models, right? It takes about 90 days to train a model from scratch. It's kind of what the general paradigm is. And so if you only have a couple of months saying Trump is president, and you have 4 years saying Biden's president, the LLM is going to say, well, statistically, Biden's probably president, right? Because it doesn't know context and dates and times and politics. It's just a lookup table. It's just a word calculator. So these models, especially the closed source ones, there's so much stuff which is hard-coded, and it's constantly hard-coded, right? And then they have to be set up against adversarial attacks, right? There's a lot of interesting stuff coming out to these days about how easy it is to poison a model. So the Anthropic folks are doing some really cool research, some fundamental LLM stuff. And they found that a model in like the 13 billion parameter range, which was trained on 15 trillion some odd tokens, with as few as 250 documents that were reintroduced, you could poison and change the output of an LLM. And that's a small subsection. And about a year and a half ago, I was curious about how this would work. So if you're curious, we can talk about this offline. I'm not going to go into great detail, but I've started to create a methodology where I can do the moral equivalent of steganography on text. And so I can write a text answer on Reddit that I know is wrong, and I know my LLM won't ingest it, but other ones will. And I can find little breadcrumbs of my experiments in the commercial models. It's a dangerous world.
You have to poison before it's picked up by.
Well, again, it's probably not that many, right? I mean, here's a disturbing statistic. 40% of OpenAI's data is Reddit. Thank you. Have a good night. So this is a good time to take a break. We got time for maybe one more question before we take a 15-minute break? Yeah. I think it's really cool. I love it. So so the question is, what do I think of NVIDIA's bfloat format? So bfloat is 16 bits, but it changes the weight between the decimal and the exponent. It puts more in the exponent, so you get more dynamic range. So instead of having 3.04, in a range of 10, to the 10th power, you could have 3.0 and a much larger range, dynamic range. I think it's really cool. And when you're using a lot of LLMs, you're actually using bfloat, and you just don't know it. Yeah, very good question. All right, well, let's take a break, and we will reconvene at 2:45. All right, so I am going to give you a little trick since people left. When you're working with models, like closed source models that have dynamic routing of models that chooses the model based on context, here's a little trick to get it to use the most expensive model always. At the end of your prompt, you add a simple line. It's ask me any clarifying question until you're 95% certain you can complete the task correctly. And that will use a reasoning engine to help you engineer your prompt so that the LLM has the greatest chance of answering your question successfully. That one trick improves your commercial LLM usage by about an order of magnitude. Works really well on Perplexity and GPT-5. I don't know if it works on Grok. All right, so we finished the last lecture by looking at DeepSeek and Llama. We learned a lot about tokens and model size and GPUs and GPU memory requirements. Now let's look at other open source and open weight models that complement what we've covered before and have specific use cases. DeepSeek and Llama are good general purpose models, but there's a lot more out there. So we're going to talk about Gemma, which is the open source Google Gemini model. And it is efficiency optimized for resource constrained environments. Mistral, which is optimized for single node deployment and specializes in both written languages as well as programming languages. Quinn has specialized domain variants, these distilled models, which have amazing performance per token on domain-specific tasks that have very strong mathematical reasoning, and they're really good for course room pedagogy. Bloom is sort of the most open model that exists. It's the model that was created iteratively throughout with 1,000+ scientists in 40 some odd countries around the world. And not only is the source code and the weights published, but also papers about how it was trained and how the data was curated and developed. Some certain niches we're going to look at. We're going to look at edge computing and some small models for IoT sensor networks, multilingual research and equitable access to LLMs. We're going to look at mathematical modeling, and we're going to look at some medical AI options. So Google in general has very efficient models. And if I were a betting man and I wanted to bet on a company who's going to succeed, Google has a pretty good justification, mostly because they don't run on NVIDIA GPUs. Do you know what they run on? Have you ever heard of a TPU? A tensor processing unit? So these are this bespoke hardware created by Google when TensorFlow was all the rage. And it kind of petered out. They really didn't mass market them. You can only consume them in their cloud. But their performance per watt and the performance per dollar is really amazing. So Google has really focused on efficiency. Gemma has some unique architectural features, including multi-query attention, which means the attention cache is preserved through multiple prompts. So it's more efficient in terms of you using it. It's a 8K tokens. It's not a huge context window. There's specialized variants. There's a code version. There's a multimodal vision language one. And there's a medical one. And just by keeping the same parameters and updating it with new data, we're able to get a 10% accuracy improvement on medical benchmarks. So that's kind of cool. Particular applications, field research, edge devices, Medical imaging. Medical imaging is one area where AI and LLMs are already making a huge impact. We've been doing, AI and imaging for a long time, a decade plus, right? ResNet was like 2012. But we're really good at image recognition, and there's tons of data around there in the medical industry. So you can do very accurate cancer classifications, right? With like 7 billion parameters, right? Very small models that you can run on a single GPU that you could integrate with a scanner. And so some of the work I'm doing these days are helping companies who are building surgical robots, right, that are autonomous. And we're building the intelligence layer and the computing infrastructure to support that. And we're putting the GPUs in the actual robot. It's kind of cool stuff. Lastly, it's really good for explaining tasks, the reasoning variants, and it's really been optimized for like STEM tutoring. So I would look at that if you're doing some course room pedagogy. GEMMA 3 added multimodal capabilities. There's a 1, 4, 12, and 27 billion parameter varieties, different context windows, different use cases. So 1 billion is edge, 4 billion is chatbots, 12 billion is for high context tasks, and 27 billion is sort of their enterprise multimodal with a much larger context. Very similar domains. In the version 3, they now support 140 plus languages for international research and have some advanced image captioning. So it automatically captions images for like accessibility, right? This kind of technology that's used a lot in websites that publish data, right? MedGEMMA is the domain-specific medical optimized version of GEMMA. There's a 4 billion parameter multimodal for text and image processing. A 27 billion that's text only, that's used for, I don't know, it's your WebMD, right? And WebMD, I don't know if you remember, but everyone had cancer. It's a little bit better than this today. And it's starting to be used because companies have just so much patient data, right, that they have. Now, the training data that goes into these were de-identified. So it did not use HIPAA data. Well, we say the data's been de-identified, but it's actually not that hard to take if you know, anyway, I'm not going to go into that. De-identified is not a technical term, it's a compliance term, right? There we go. That's a much more PR way of saying that. Some updates we saw just by updating the tuning with new data. We see a 15% improvement in MedQA, 15 to 18% improvement in X-ray classification, complex evaluations in these agent-based multi-step workflows went up by 11%. And again, you're running these on your own hardware. But just because it's open data and you can run it on your hardware doesn't mean you can feed HIPAA data into your system on your public HPC system, right? You still have to make sure your system where you're running these is HIPAA certified or PII or PHI, right? Whatever type of data you have. Mistral. It's 123 billion parameter models, and a lot of work has gone in for single node optimization. Because they made the decision not to support multi-node workflows, they're able to do some architecture and some optimization that you couldn't do otherwise. Because of that, very good per token, and it competes on par for code generation tasks with models that are an order of magnitude more parameters. It supports 80 plus programming languages and only a dozen of spoken languages. One of the interesting use cases of Mistral, and I was talking to Graham about this and a couple other people during the break, is it's going to eventually, one of the use cases, it's going to replace legacy programming. So a lot of areas where they're starting to see advantages of this is replacing COBOL developers, right? COBOL is still used in a lot of mission critical applications, and COBOL developers are notorious for retiring early, 55, 60, 65, and then contracting out their services for 10 times what they were made because no one knows how the COBOL works. Well, that's one area where they're able to, charge a decent amount for the services, but provide a value on return. And that's just an interesting thing overall. Very few of these activities today have ROI. It's something like 95% of all AI pilots never generate a return on investment. except for NVIDIA and the cloud providers who sell the services, right? During a gold rush, it's good to sell shovels, right? You don't want to mine the gold, you want to sell the tools so other people can chase the riches, right? Mistral, to give you some idea on its performance, 84% on a general reasoning. Code generation ranks second only to GPT-4o. Grok is not included here. Grok is supposed to be very good at code generation. I have not tested it. Mathematical reasoning, it has enhanced capabilities and does really well on advanced maths benchmarks. And as I said, supports 80+ programming languages. Because it's single node jobs and because of its architecture, it has very predictable resource usage. So it makes it really nice to use on Slurm. It's really easy to write a job that runs on a single node on Slurm. You don't have to worry about MPI. You don't have to worry about multi-node communication. And if it once ran on this node within this fixed GPU memory, nothing I'm going to do is going to make it overrun that GPU memory. We're going to talk a little bit about frameworks. It has native VLLM support. VLLM is one of my favorite frameworks. And it has NeMo integration. So we were asking about earlier how you train these models. NeMo is one way. And with Mistral, you can work with NeMo and bring your own data and create your own optimized version of Mistral. Quinn 2.5 has domain-specific excellence in STEM fields. There's Quinn 2.5 base, which has 500 million parameter model, 500 million, really small, all the way to a 72 billion parameter. It had an 18 trillion token training data set. Quinn Coder is then based on Quinn Base, which generated 5.5 trillion of custom code tokens that are then fed into Quinn 2.5 Coder to update it with improved coding performance. And then Quinn 2.5 Math has a similar concept for mathematical reasoning. Great at code generation per unit dollar per unit watt. It has the most performance per token, better than Mistral for most coding activities. It has a self-improvement pipeline for complex mathematical proofs. It has a way of checkpointing and restarting its own self and verifying individual steps, which is a really cool novel approach. Almost 30 languages it supports today. It has enhanced JSON support and has ways to generate tables automatically for sorting and doing data analysis, and has some nice formatting options for automating a lot of your pipelines. Because of the way Quinn and DeepSeek work, it has significantly lower training costs compared to the other models we're talking about today, supports the frameworks, and it's Apache 2.0 licensing for most variants. Bloom is the open model, 1,000+ researchers, 70+ countries, more than I thought. It was 46 languages it supports plus 13 programming languages. That's the 46. It was the first 100 billion plus parameter model for many underrepresented languages, right? We talked about Bloom for equitable access, as well as support for non-Western scientific traditions. It's not very efficient. It scales poorly. Almost every model we'll look up today will have linear scaling to 64, 96 or more GPUs. Bloom doesn't have linear scaling at all, even on small systems. But it's an open model. To give you an idea of some results, so general reasoning, we see DeepSeek v3 is really good, but look at Quinn 2.5. This is 1/10 of the parameters, and it's beating all these other models. Mathematical reasoning, well, we saw Llama 3.1 was really good here, but what did we learn? Llama is overtuned on mathematical reasoning, and then when it gets to the advanced task, right, it craps. That's because it's overtuned. Other ones that are really good at mathematical reasoning, Gemma 3, 27 billion. And again, Quinn 2.5, 72 billion. Pretty good models. Advanced reasoning, Gemma 3 is really strong there, along with Mistral. And then code generation, Mistral, and then some more overtuned Llama 3.1. All right, so One thing I've really harped on is experiential or project-based learning and how we bring this pedagogy into the coursework. So GEMA, its really low memory requirements and some of its mathematical reasoning is nice for classroom environments. Quinn is really great for mathematical pedagogy and understanding how problems are solved, and multilingual underrepresented education, Bloom. In scientific computing, Quinn 2.5 Coder is great for small resources and supporting a lot of users. Quinn 2.5 Math provides detailed mathematical explanations. If you're doing multimodal learning, the medical GEMA, PalyGEMA, works really well. And GEMA 2B is just really nice for playing around, right? That's something you can run on your phone, right? Some unique capabilities where you might have interesting use cases is there's a version of GEMA which is called recurrent GEMA. And it has a different architecture. It's an RN plus a local attention hybrid design. And remember, I told you that GPU memory utilization scaled quadratically as context link. With this novel architecture, it scales linearly. So it's not as performant, but you can reduce hallucinations and process long document context windows more efficiently with this relatively memory efficient model. And then Mistral is just great for single node HPC uses. And it maintains, parity with the best commercial models today in terms of coding. So let's look at where we are with these models. MegGEMA, 10% accuracy improvement over the baseline. GEMA 2B, mobile IoT deployments. Quinn 2.5, it also has tool integration. So it's really nice for automating a lot of complicated pipelines. So let's talk about frameworks now. So far, we've talked about models. And models are nothing more than text files with a bunch of numbers in them. They're model weights, right? They're parameter. We still need some way to run the model. And to run a model, we need a framework. So we're going to go over a couple of different frameworks. We're going to go over GUI applications as a low barrier of entry to start prototyping these. We're then going to talk about command line engines for high performance serving and running batch queries. And then we're going to look at ways of doing IDE or notebook extensions for coding assistance with open source models. In general, you start with GUI tools for rapid prototyping and model evaluation. Once you've chosen a model you want to look like, you maybe move to a CLI tool with a different framework for optimized versions of the models you chose. And the framework you choose for your CLI tools depend upon the models you're going to use, right? Different frameworks support different models at different levels of completeness. Then you'll use CLI engines for running on Slurm and multi-GPU systems. We'll talk a little bit about IDEs and integrating them, and then we'll wrap up talking about RAG platforms and how to bring your own data into your queries. LM Studio. How many people are familiar with LM Studio? Yeah, LM Studio is a cross-platform Mac, Windows, and Linux GUI. It natively supports Apple Silicon, so your M chips. It also supports newer Intel Macs with the AVX2 instruction set support. Windows native support for x86 and ARM. Linux is x86 only. It does not have ARM support. Core capabilities, it has automatic NVIDIA GPU detection, and we'll just use it if it's there. You don't have to install a different framework or anything. It just works. It has direct integration with Hugging Face. Does everyone know what Hugging Face is? Hugging Face is like Docker for LLMs. So it is a model registry. And on Hugging Face are 45,000 some odd models that people have developed or tuned or optimized for specific use cases. And you can just download those weights and use those models. It has a built-in OpenAI compatible API server. So that means you can fire up LM Studio, you can choose a model, you can spin up an OpenAI endpoint, and then you point your VS Code or your Jupyter notebook to that model, and you can use it interactively. Or you can write some curl and hit an endpoint, or write some code and use the endpoint, right? It has a plugin architecture. Today, the only plugins are RAG, TypeScript and JavaScript support, and Wikipedia for just querying Wikipedia data. They are eventually going to allow you to develop custom plugins. It's currently a closed beta. And if I had to guess, this is probably their monetization approach, right, for building your own plugins. But I don't think that's been announced yet. So if you're on an HPC system and you spin up a virtual desktop on Open On Demand, right, you guys have access to Open On Demand, you can run LM Studio. Right? It will run on CPU only. But if you can do virtual desktops on GPU nodes, you could also use your GPUs. AppImage is a way of installing it in user space. You can just install it. You don't need access to it. It's just a binary you drop in and run. You can build from source. They are in your package managers. So if you're using Ubuntu or Debian or Arch or Nix for some reason, they're upstream as well. Arch and Nix are really cool operating systems for people who don't like to do work, right? You can play with your system all day and not actually do any science. And then Snap, if you're familiar with Snaps in Apple, which is a repository for enterprise Linux, right? Red Hat, Rocky, Alma, etc. They're in those as well. But if you're just a user on a system you don't have root access to, just start with AppImage. So you can do within your LM Studio side-by-side evaluation of different models. You can choose a model 1 and model 2, right at a single prompt, and they'll run and you can compare the results. And you can kind of use this for model evaluation. It supports interactive adjustment of temperature, top P, and context link. Context link we've talked about, right? That's the context window. Temperature is the randomness. If the temperature is 0, it's always going to produce the most probable next word. It becomes deterministic. But usually you have that temperature cranked up a little bit, so it seems more like natural communication, right? You use different words. And then top P has to do with phrases. It's kind of like temperature for phrases. And the higher top P is, the more creative and flowery the language is. The lower the top P, the more reproducible and consistent it is. More statistical likely. And statistically, most people suck at writing, right? So most of the data that's been trained on is pretty simplistic. It allows you to batch multiple prompts. So you can bring up a bunch of models you want to try, query up a bunch of prompts, go to bed, come back the next day, and get the results. It automatically detects and loads across multiple GPUs, shows you GPU and memory utilization, and has built-in support for all the quantizations we've talked about. Now, LM Studio is not a framework. LM Studio is a client that attaches to a framework that runs the model. The framework behind LM Studio is called Llama CPP. And Llama CPP was originally written to support Llama, the open source model, and it's a standalone C++ program. No external dependencies, no PyTorch, no Python, thank God, right? You just install it and run. It's a single source. It supports the GGUF format, which is the universal quantized model format, supporting multiple quantizations. That is, a single model file allows you to dynamically run at multiple precisions. And this is the same format that is supported on Hugging Face. Single file contains weights, etc., and it works across platforms. So it's system agnostic. OLlama is a command line client for Llama CPP. And it works like Docker, in that instead of Docker pull, it's OLlama pull. Instead of Docker pull from a Docker registry, it's OLlama pull from Hugging Face. where using Ollama, you have access to the 45,000+ models on Hugging Face. So basically, you just specify hf.co, the username, the repository, just like GitHub, right? And you can pull down models. It supports Git-like model versioning with automatic updates and rollbacks as you go through a pipeline. And it has access to a lot of the domain-specific models we've talked about today. So far, we've prototyped at a GUI. We've chosen a couple of models. Now, we've used Ollama. We've played with it a little bit more. We've got some Slurm scripts running at the command line. But now I want performance. That's when you look at other frameworks. One of those is VLLM. It has a very nice page attention mechanism, which allows dynamic memory allocation depending on the context windows, so it's more efficient. It's dynamic memory allocation as opposed to static, right, for a lot of the stuff. It allows continuous batching, so you can batch some things up, it can start processing those, and then you can batch up some other things to be done when those are done. A lot of things like LM Studio, you batch up, you have to wait for that batch is done before you do another batch. As I said, it's CLI driven, great support for NVIDIA, and one reason I like VLLM, it's the framework that's open source that has the most robust support for these new Grace Hopper and Grace Blackwell unified memory architectures. And I'm really big about science per dollar and science per watt. And nothing beats Grace Hopper and Grace Blackwell for tokens per watt for RAG and LLM workflows. VLLM, you can install via pip. You can install via Conda or Mamba. You can install from source. There's containers out there you can run today. There's an all-in-one installer script. I would not run this on an HPC system. If you want to run this on your local machine, sure. HPC system, use Mamba or use Aptainer. So why would you use VLLM over native Hugging Face? Well, Hugging Face has its own framework called transformers. VLLM has about a 2.5 times performance improvement over the Hugging Face transformers framework. It also has a huge reduction in key value cache memory usage and shows linear scaling across, I think, 8-way nodes. That'll be up in a little bit. There's 200+ architectures supported, including all Llama, DeepSeek, and Quinn variants, as well as partial support for some of the more medical and cheaper models we talked about. SGLang is the framework developed by the DeepSeek folks. So if you're running DeepSeek, SGLang is the most performance for DeepSeek. So here's some good examples. So SGLang, 52,000 tokens per second. VLLM, 35,000. TensorRT is another framework. And I just kind of find it's okay at everything. I mostly have other use cases for the other frameworks. Oh, VLLM is linear up to 32 GPUs, so 4 8-way nodes. Tensor is 64, SGLang is 96. The other good thing about SGLang is it has day one support for new DeepSeek models, because that's the framework they use. So, both LM Studio and VLLM have a way to spin up these OpenAI compatible API servers that you can consume in Jupyter Notebooks, RStudio, VS Code's AI coding assistants, or any of the forks of VS Code which have opinionated updates. So when choosing a framework, it kind of depends upon what you're going to be doing. If I'm running DeepSeek models, I'm going to use SGLang or VLLM. And it kind of depends if I want to run other models as well, and I only want to learn one framework. Llama, don't run Llama. But if you do, VLLM, or if you want more performance, you can learn TensorRT, but there's almost always a better model to pick than Llama. And as I said, I think the Llama line's going to die, right? So might as well pick something else. Rapid prototyping, Ollama is great. VLLM also has a lot of model support if you like VLLM. Maximum performance, SGLang for DeepSeek, TensorRT LLM for some other models. Huge scaling, SGLang. Most model options, VLLM. So here's my opinionated chart on how things work. Llama CPP runs almost everything except Bloom with limited support, but it's just okay, right? It's just C++ that someone wrote from scratch. It doesn't leverage any of the Python and the highly optimized stacks. And here's a little secret, which I didn't talk about too much earlier. NVIDIA, the containers that are in GC, the NVIDIA GPU Container Cloud, they take open source products like PyTorch, and they make optimizations to it that, depending on the license of the software, they don't often re-release to the community. So PyTorch versus NVIDIA's PyTorch can have different performance characteristics. And so if you're going for maximum performance, try to use the NVIDIA ecosystem if you have access to it. Yeah, so that's just kind of like the decision matrix. RAG pipelines. So one of the big problems we have is, of course, with LLMs is hallucination, or data that has been updated or released or published since the LLM was trained, right? And so the first way of doing that is with RAG, and this is resource augmented generation. And the way RAG works is you take a document and you tokenize it, or you create vector embeddings of it, which takes all the words and everything in the document and converts them to something that can be done with a semantic search. Then you write your prompt to the LLM. Then the RAG software evaluates your prompt, tokenizes it, and then searches through your RAG vector embeddings and picks out the ones that match or the most relevant. It then injects those vector embeddings into the prompt that go to the LLM to give it additional dynamic context. So that's cool. So you can bring in your own documentation, your own information, right? You can drop scientific papers in there and query it, right? You know, a lot of what I do is I copy images or tables and I tell it to extract the data from it, right? And then convert it to a CSV file as opposed to like retyping stuff that are only images. Really good at that type of stuff. Also, of course, reduces hallucinations by giving it additional context. RAG is an intermediate step. It's not the solution. Now, if your data sets are static and that you only need a little bit of data to give it context, then you can do RAG for life. But data is always being updated. And your RAG pipelines or your RAG vector database can't increase ad nauseum because you're going to scale the context window. And you're going to limit your, if you get too much, if you're either going to overload the model with too much context window, that's going to scale the GPU utilization quadratically, or you're going to leave out results in your search because there's not enough to shove into the context window. So eventually you'll get to the point where as you gather enough data, instead of post-processing it with RAG, what you actually do is fine-tuning. That is when you open up the black box and take your data and incorporate it into the corpus of the model. That is, you twiddle bits, you twiddle parameters to capture your new information you add to it. But that is very computationally expensive. And we're not, most projects just aren't there yet. That also is an intermediate step onto ultimate production. And where things are going today are agentic workflows. And that is the data for the model is generated on the fly by query agents. So you'll have an agent that speaks your email. You'll have an agent that speaks your Slack. You'll have an agent that speaks Wikipedia, or it's a plugin for LM Studio. And then on your query, your LLM that you interacted with is not really an LLM. It is something that determines the order of operations in which agents to call as part of a chain. But we start with RAG. So we drop in PDFs, doc files, text files, CSVs. If you have a multimodal model, you might be able to use a video or an audio. Has anyone ever used NotebookLM by Google? Yeah, notebooklm.google.com. You can spin it up, and you can give it data, and it can query it. It can tell you about it. It can generate a podcast, because that's what we need in the world is more podcasts. I'm not a huge fan of tariffs, but there should be tariffs on podcasting equipment. I think that's a big part of the downfall of our society. We should get rid of podcasting. Anyway, we then will need a vector database to store these embeddings. We're going to cover 3 of them, ChromaDB, Weaviate, and Quadrant. And then the LLM produces a response via the normal framework. It's just been given additional input to your query that was generated from a semantic search against your vector embeddings on your own data. Cool? All right. LM Studio has built-in RAG. The built-in RAG isn't very robust. It's 5 files maximum and 30 megabyte combined size. But you can just drag and drop PDFs, doc files, text files, CSVs. It's getting to the part in the day when my voice is going. It's an easy way to get started. So when you do RAG, there's actually multiple ways of doing it. There's something called CAG, and then there's RAG. And CAG is just when you dump your entire document in there because it's small enough that you don't have to worry about downsampling it. And then RAG is where you do semantic searching. It also has citation integration. If you ever use Perplexity, right, you get a result and it will tell you the citation where it came from. LM Studio does that also. It'll tell you where in your document it found that information. So it's a really cool tool for just doing search. I don't know if you've noticed, but basic search has been broken for the last several years. In 2019, Google purposely made its search algorithm worse. Do you know why they did that? More ads. Too many correct results in the first search. So Google used to do its own version of semantic search when you did a Google search. So if you search for pants, it'll also search for trousers, right? It got rid of that in 2019. You said you search for pants, here's pants. You want trousers, try again, so we can serve you more ads. One of the major use cases I use AI for in LM Studio is just to have a better search, because you can't organize data anymore. And Google trained us, a decade plus ago. They said, don't sort, right? Don't micromanage your emails, just search everything. And then they broke search because they want you to pay for LLMs. So what else? So the built-in capability is, again, these file formats. It also has a vector DB plugin where you can point LM Studio at different vector databases, and you can add support for other formats, including Excel. If someone was over there talking about Excel earlier, support for images and audio, etc. It has an internal database, again, with these limitations, but it can use external vector databases. The built-in capability only supports text. With other vector databases, you can get multimodal support. No audio, but you do have audio support with different vector databases. The 3 databases we're going to look at is ChromaDB, Quadrant, and Weaviate. ChromaDB, no setup. LM Studio can install it for you, or you can run it in a container. And it's great for single prototyping, but ChromaDB is limited to single node only. It uses a local file as a database, and if you try to access it in multiple nodes, you'll get race conditions and file locking, etc. Quadrant is more like a traditional database. It allows concurrent access, and it's much higher performance and works on single node and multi-nodes. And again, LM Studio can install it. Weaviate is what you use if you're building an open source, more enterprise or more like research group solution. Weaviate supports built-in clustering, sharding to put data on different nodes, has high availability and failover. It has support for all kinds of features, including RBAC. RBAC is role-based access control. Here's something really funny about RAG. Let's say we're working in the enterprise, right? And we've gone through and we've done all this work so that Susie in engineering has access to different data than Bob in HR. And then we take all our company information, put it in RAG, And now any query can get access to any data, right? Because there's no RBAC, there's no role-based access control. So Weaviate allows you to set up essentially credentialed access to different data sources. So instead of having different vector databases for all different subsets of data people are allowed access to, you can do it in one centralized way and then say what user has access to what data to query for their RAG pipelines. 99+% of the use cases in here, Quadrant will be sufficient. All right. Lastly, I want to talk a little bit about Podman. So Podman, again, container based on Docker, but it is rootless operation, runs in user space, no daemon. Uses the same command line syntax as Docker, so it's good for that Docker pedagogy and unifying tool sets. However, it also has a path to Kubernetes in terms of the workforce development space. So Kubernetes' main feature is what we refer to as orchestration. Orchestration you can think about like as a distributed operating system across multiple nodes. And you know that X number of these containers have to run, and if one goes down or a node goes down, it automatically spins it up somewhere else. Podman has some of these orchestration concepts. And so with Podman, you can create multiple containers that interact together. So you could have a container that spins up your vector database or a container that spins up a traditional SQL database. And then you can run your workflows all containerized and have them communicate. And that gets you half the way there to learning Kubernetes. So TLDR, if you're at the development stage, Podman CLI, fine for dev test and container fundamentals. This is going for production on a large system. Single node, Quadlet, or systemd. This teaches you the concept of starting services and using Podman to run services. And it's good to learn service orchestration. When you start going to multi-container workloads, then you bring in the concept of Podman pods, which work a lot like Kubernetes pods, and allows you to really start talking about orchestration concept at the service, at the microservice level, as opposed to the system service level. And then finally, production. All of these are run in production at Kubernetes. Don't learn Kubernetes unless you really want to get into IT, but it's pretty cool stuff. So start with LM Studio on Open On Demand, locally, or another VDI. Migrate to Ollama for test dev of advanced pipelines. Implement VLLM with either Conda or Mamba, if you want to use those traditional tools, or Podman. If DeepSeek is being heavily used, consider adding SGLang as your framework support. Then gradually increase your RAG capabilities. Start with LM Studio, add on ChromaDB or Quadrant, and then longer term, if you need it, either Weaviate or Kubernetes, or instead of doing RAG pipelines, learn about fine-tuning, or learn about agentic workflows. And I'm done. Thank you very much for your time and attention today. And I'll now take questions.
Agentic overflow those RAG pipelines. So how do you usually solve performance problems? Sometimes in my personal experience, the RAG pipelines tend to be very slow.
Yeah, so the question is, when going from RAG to agentic and you have performance problems, what do? RAG tends to be very slow. And the reason RAG is slow, are you running this on your own hardware or on like commercial models? Like using OpenAI, or are you running it?
And sometimes if I'm I am using the tree embedding and the random model, calling API. So yeah, it is still slow.
Yeah, yes, it is slow, right? So RAG is not necessarily high performance, right? Because you're adding additional steps. You're adding a transcoding step, you're adding a vector embedding semantic search step, and you're dramatically increasing the size of your context window. So think about when you type something into a prompt. It's a paragraph, right? couple hundred characters, maybe 1,000 characters, right? There are roughly 4 characters per token, so 1,000 character prompt, which is pretty big, that's 250 tokens, right? When you're searching through your RAG, your vector embeddings could return 100,000 tokens of your search results that get inserted along with your prompt. And then it's not just the 1,000 characters or the 250 tokens it's processing. The model has to process all of those 100,000 tokens. And we talked about memory scaling, but computational scaling scales linearly to non-linearly as the size of the data you're providing to it, depending upon the model, the architecture, whether it's dense or whether it's hybrid. But it's more computationally expensive as well. So you're asking the GPU to do, or your CPU to do a lot more work. And it's not just twice as much work. It could be an order of magnitude more work easily. Yes?
I'm just curious, like, could you comment on like how agnostic any of these LMs or ways to use LMs are to like any sort of input data that you might have? Like, for me as a scientist with a specific, database that's like maybe not huge, that I, have specific questions to answer. If I'm trying to decide a bunch of machine learning models to use that would be, the best predictors for, whatever output variable I'm interested in. Like, maybe a random forest is adequate for my needs, but maybe like I could just fire up one of these things and then, does it like kind of spit out a prediction that I could then, assess, or how, if it doesn't, could I tune it to do something like that?
So
I don't know if that would.
I'm not sure I understand your question. Can you repeat it again or with slightly different words?
Yes, for those.
So what research do you do?
What research?
Mm?
Oh yeah, I'm a
What?
microbiologist.
Microbiologist, okay.
So,
And so what are you trying to do with LLMs?
which microbial sequences are best predictors for plant pathogens?
Okay. And what sort of data do you have?
So I've got like a flat file, a text file that contains counts or transform counts of specific microbial sequences, and then I've got an output measure of how many
Quantity of interest. Okay, so let's abstract this, right? You have multiple input sequences, right? And you have multiple output quantities of interest. And the quantities of interest are consistent around the models, but the sequences are different. And you're trying to figure out, if I want this output quantity, what's the best input for it?
Yeah.
Okay. So it's an input-output map in reverse. You have a desired output, you want to find the input. So typically that's an inverse problem or an ill-posed question in traditional mathematics. And so it can be complicated. And LLMs are very good at pattern matching. That's all they are, right? And so I could see it being useful. I don't have a good gut feeling for what that is. And unfortunately, again, a lot of LLM usage these days is just playing with it and trying to develop that intuition, that gut feeling on what's good when. And I mean, basically right now, there's so many variables on input and output and model and transformer and hardware that we have not done enough projects to be able to understand what happens generally and abstract out best practices and principles for model selection. So right now, it really is just intuitive and that layer below your conscious where you just kind of get that tingling feeling, right? I wish I had a better answer, but it's very experimental today.
Yeah, thanks. And I assume this applies to anyone who has slightly different types of data.
Yeah.
Or, any feature selection problem.
Yeah. And feature selection tends to be better with more traditional methods. Yeah. Other questions? Yes. I don't know. I don't do pair programming. No one wants to program with me. Most of my programming happens really late at night in obscure languages. So let's think about that a little bit. What would be a good environment for pair programming? Well, first, you'll want to use the same model, right? You want to use probably different instantiations of the model. You'll want to share a repository, And you'll probably want to share as much tooling as possible in order to really have shared experiences. But for me, I would rather do one IDE with multiple people having view access to it, and you're just on Discord, right? Or whatever communication platform you use. I didn't mean to reveal my inner gamer. Let's say Teams. There we go, Microsoft Teams. You get on Microsoft Teams and you talk and you just share the development environment. That's where I really find. And then otherwise, I'm a big fan of individual development, fork, pull requests, and code reviews that are done together. But I personally haven't found much use of programming together as peers. I think it's good for pedagogy and student-mentor relationships, but the stuff I tend to work on tends to be very complex. Computational quantum mechanics is weird, and there's, I don't do a lot of Python and data science and stuff that I can just share with people. That's just not what I do. That being said, I'm in a couple of Slacks where I have people who do this kind of stuff. I'll ask a couple of my communities for some prompts in pair programming, and I will email Laura or someone here who can share it with the community. Or if whoever asked that question, you have my email address on all 3 slide decks, send me an email, and I promise I'll reply eventually. I am traveling the next 6 weeks in a row, but sometime in mid-December, I will get back to you. But good question. Other questions? Yes, Thomas.
A lot of the research still uses the fundamental kind of approach of using these open REST models. What's your take on it?
I think we're kind of hitting the limitation of current technology. And I kind of think, the question is, what do you think about the current state of autoregressive models and how they're used in LLMs, and what do you see as sort of the future? In general, I think we're getting we're kind of hitting the limits of the current architecture. For a while, when we started, we had 10 billion parameter models, then 100 billion parameter models, and the rate of convergence on the benchmarks looked promising. But when you only have 2 data points, everything looks like a line, right? Now we have 500 billion parameter models, 1 billion parameter models, 2 trillion parameter models. And we're starting to get enough data points that we're seeing this turnover. And we're seeing it asymptotically approach a correctness that's at or below 90%. It's very rare you see something on any benchmark that's beyond 90%. When you do, it's 92, 93, and tends to be on coding benchmarks, because coding is one exercise in which there's tons of data out there, and due to the nature of the people who program, if you make a mistake on Stack Overflow, you will get publicly embarrassed, right? And so there's that entire ecosystem around people correcting each other. That stuff tends to be better than philosophy, right? But because it's only approaching 90%, we really need to think about new and novel architectures. And I really don't think we can justify the current valuations of all the companies out there if we're only a 90% success rate, right? I was talking about this during the break. But the future, as we talked about, is agentic workflows, one for security reasons, one for flexibility of the agents, one for being able to update them with dynamic data. The current valuations of all these companies are based on replacing labor, right? The only way NVIDIA is worth every pharmaceutical company combined in the world is if this does something. The only reason ChatGPT and OpenAI companies are worth something is if they replace labor, because that's the evaluations that private equity and venture capitalists has put on this. But if we start strapping these agentic workflows together, we get the product of probabilities, right? So 90% success rate 4 or 5 times in a row. Well, 1 shot is 90%, 2 is 81, 3 is 72, 4 is, right? And now we're at 5, we're in the mid-50s. And that's a 90% success rate, right? 95% success rate, I don't think is obtainable, at least today with the current architecture and the lack of data. It's a data problem, actually, for the transformer architecture. But I don't think there's another order of magnitude of data out there to get us past this. So I think we need some actual research, and I hope to see some novel new algorithms be developed that sort of replaces what we're doing now. Sure. Yes. Which one? That one. Okay. Questions? Yes.
So, going back to the scale question, I've seen one of the solutions proposed be agent swarms, where you just throw enough agents at it that they will find their way through. Do you see that as any solution to that?
I do see people interested in ensembles of agents that take a more statistical approach. And then you kind of have a quorum type approach. So there's a company in Germany that I'm doing some biz dev with who are trying to create Bioplexity is the name of their product. So Perplexity for biomedical applications, healthcare. And they have Biomed Advisor, which is trying to be the WebMD for agentic models, right, for LLMs. And what they're doing is every query, they're hitting Anthropic, OpenAI, they're hitting some llamas, some self-developed ones, and they'll take all these models together and then summarize the results and do sort of like a voting mechanism. That to me is not necessarily the most elegant solution, but it might be the quickest path to market. And NVIDIA would love that, because instead of using, 8 GPUs per query, you're using 40 GPUs per query, right? And all these statistical approaches to brute forcing and basically sampling out the errors is not going to be sustainable from a power, cooling, hardware, and cost standpoint, right? But I think if we do a bunch of sector-specific models with novel training on small parameters, that could be cool for limited edge cases for specific cases. Yes? DeepSeek. DeepSeek R2. Oh, no. DeepSeek R10528. DeepSeek R2 is really cool. Question?
Pre-process the type specs.
With time series data, what's the question? Can you speak up a little bit?
Concerning time series data with circular statistics, what law is best? How do I pre-process the time aspects?
I don't know if I'd use an LLM for that. LLMs don't replace everything, right? Sometimes we have to just sit down and do it. Time series data is very regular. There's lots of well-established mechanisms for working with it. That's what I would do, or tell a student to do. Next question.
Going back to that temperature thing and setting it to 0 and getting outputs, is that always deterministic, or is there a hardware component that makes it non-deterministic?
That's a really good question. And I don't think enough work has been done on that. So I showed you earlier when I was doing SPAC and compiling PyTorch from scratch, I added the Arch equals SM80, right? The specific architecture for the Ampere GPU, right? And one of the exercises I'm hoping to do in the next year and publish as a paper next year is to take models with low settings of PTOP and T and see if different frameworks and different hardware give different results. And then if they give different results, if I compile for Ampere but run it on Hopper and Blackwell, do I get the same or different answers? In theory, they should be the same. Caveat round-off error. And if we were working at FP64, it would be the same. If we're working at FP4 and we're introducing architectural uncertainty and newer versions of software, I could see cases where it's not truly deterministic. In that, well, it is deterministic for every combination of software and hardware. But if I change the software and the hardware, in terms of the software version, but not necessarily the software I'm running, I don't have a good intuition whether it's 100% deterministic or not. And so there's another company I'm doing product development with who is developing, chat GPT-like capabilities, but your own hardware with open source models. And we are doing like governance, and we're saving the state of jobs, and that we're saving some of the mathematical representation so we can replay that workload without storing the entire conversation. That's one way we're doing it. Another way I'm doing it is I'm working with a checkpointing company that's helping to come to market. So checkpointing is saving the state of a running job to disk and then resuming it later. And so I'm interested in binary reproducibility. That is, I instantiate the job and I put a wait at the beginning and I snapshot it in GPU memory and save the binary representation of everything. And then I run the job. And at that point, it's by definition reproducible. It's also a good way to cheat licensed software, but I didn't say that. All right, we got time for some more questions. I think we go for what, like 6:30? Is that how long we're here today? Yeah.
Be the way to go if you're focusing on a single node.
Single node encoding.
Where's the lowest bound that, like, just an A100 be sufficient,
Oh,
or does it need to be?
It'll be multiple A100s, right? It's I think it's a 122 billion parameter model. So if you run it on an A100 that's FP16, right, which is 240, roughly 300 gigabytes of GPU memory. The high-end A100s have 80 gigabytes of memory, but there are nodes that have 4 and 8 of them in there. So if you have a 4-way node, that'll be 320 gigabytes in a SXM form factor. These are these unified memory high-speed interconnect nodes. That will work with Mistral very well. But you could run it on half as many hoppers because it's FP8, or a fourth as many Blackwells.
Where do you get those?
Well, hopefully, Cambridge Computer. We got them for sale. Well, you can buy them. We won't be able to ship them to you until like February, March because of supply chain issues. But yeah, so other questions? We got any more on? Okay.
Of the expert seem to be more logical way of classifying, of using a particular LLM or a particular model for a type of problem. So why is it not implemented as extensively?
Why is Grok implemented as what?
Why is it not implemented as extensively in different models?
Oh, so MOE is sort of the way most models are being architected today. There are some novel hybrid designs where they just refer to as MOE hybrid, but they don't really release the special sauce. So it's really hard to know what they're doing on the closed source side. And so all I can tell is look at the source code for the open side, right? And we know what they're doing there. But these days, there's really no reason to build a dense transformer model, right? Unless you're doing a very small model that's tuned to do one thing, where every MOE would essentially activate only one model, right? But when you're building these general purpose models, you're capturing all the world's data in a single model. And each query is going to access a very small subset of that. So MOE is definitely the way forward. Same memory utilization, but less compute time. What would be really interesting is a preprocessor that analyzes what MOE path it's going to do and then instantiate that subset of parameters in memory. And I'm working on that. Well, so the pre-processing model is a classified problem, right? It's a classifier. How it works on the closed source side, again, they don't release that. And when GPT-5 was released, they just sold it as one model. They didn't even tell us there were multiple ways into that model. And so they don't even release that stuff because they're constantly changing how that routing model works based upon their current demand, the number of GPUs in training versus inference, and them trying to lose less money per unit time. Because all these companies are losing tons of money, right? The bigger plan you have with one of these companies, the more money they use per person. The $200, a month plan at Anthropic, they're losing tons of money on those developers. And even on the $200 plans, they're starting to put API limits. Other questions? Do we have anyone online? No? Okay. All right. Well, last chance. Speak now or hold your peace until happy hour if you go. Yes.
Get things from your RAG database into your prompt, but the material rejection could easily have also come from inaccurate. So the base models are a way to verify that the RAG information has been used to generate your output. So like, for example, with a building fire escape plan, a base model can generate an error one. But if you input like an actual one, your RAG interrogated, you verify the sense it's getting out from your rejected data.
Yeah. So the question was, when you're adding RAG data to a query and you get an output with a recommendation, how do you know that wasn't created based on the corpus in the model versus in your RAG data set? And the answer to that is citations, right? You want a model with citation support, and then you can ask it, where did you get this information? Or it'll just show you the citations. Perplexity shows you the citations. LM Studio has a way of showing citations, but citations are the answer. Now, the question is whether the model's lying to you or not. That we don't know for closed source models. Yes?
How reproducible are the medical recommender LLMs? For example, the order of training sets can influence the end result. Do they version control the order of the test?
So, in very few of the models do we know what they do for training. Even the open models tend to be open weight models and not open source or open recipe models. In reproducibility and how good the classifiers are, in imaging, really good. Medical imaging is something we've been doing with more traditional AI methods like neural nets, ResNet type stuff. And we just have such a huge data set that's already labeled. Cancer, not cancer. Cancer, not cancer. And we're just really good at training image-based models because healthcare is a very profitable industry in the United States. And there's tons of motivation for automating it and reducing costs on their side. And so because of that, that's one sector where it's really good. Also, if you think about it, what an image is going to look like, there's only so much variations. It's always going to be the same number of pixels. It's always going to be the same number of size. It's always going to be a picture of the same body part. It's always coming from the same image. So your number of variables is really reduced, and you're reducing your problem complexity to only a few variables, as opposed to diagnose this patient. Whether that's accurate or not today, I have no idea. That's not my area of expertise. I just know it's usually not lupus, if you like house.
So you're just talking about is there image segmentation in any way, or is that better using other methods?
I think right now it's better with more traditional. So the question is, are LLMs good at image segmentation? I think traditional pipeline tools are really good these days. The only justification would be speed up and reduce of computational cost. And I don't have a good understanding of the size of model I would need to replace it and what the computational complexity of the two. I could see them going to something to save money in the commercial space, but the traditional pipelines are so well established, I don't think there's justification from a science standpoint to replace them today. All right, my voice has a couple of more questions left.
Hold there. Awesome. I do have one more.
Okay.
So when I'm doing some AI paired programming and I'm using, say, Claude, and it says you're hitting 95% of your context window, and that says hang on, and it starts ratcheting that down so that there's more available. What is it doing?
LRU, least recently utilized, is getting evicted from memory.
Stuff like that.
Yeah. Just reducing context. Now, there's some interesting philosophical ways you could do it, right? What you could actually do is create dynamic small parameter LLMs on the fly to reduce the data in the context window. And then when you do an agentic pipeline and do a query, you could farm off a query to your reduced representation. I don't think performance is there yet, but I think in about 36 months, 2 generations, we'll have that capability. Right. Any other questions? One more. All right. Thank you, everyone, for a great day.